Hi everyone, my name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. Today I'm gonna show you how to build a few amazing blockchain projects. We will build decentralized applications using Ethereum and Solidity. We will of course start from the very basics, and I will show you the fundamental concepts behind the blockchain technology, decentralized networks and smart contracts. Along the way, we're going to discuss the strengths and the weaknesses of the decentralized systems, and by the end of the course, you will gain the skills to design your own blockchain applications. Please make sure that you watch this video until the end, and if you don't understand something, either stop the video and repeat or write it down a comment. I usually respond to all the comments that are written under my videos, so I'll be more than happy to help you out. If you like this completely free tutorial, please make sure that you subscribe this channel, and also you can access the full code for this tutorial from the GitHub repository that is linked in the description. Now let's jump straight to.
Fundamentally, a blockchain is a data structure. It's like a soda can, but instead of holding fizzy goodness, it contains a list of blocks filled with transactions. Each block is linked to the previous one, creating this neat and tidy chain, hence the name blockchain. This structure ensures that once data is added to it, it becomes incredibly difficult to alter, making it an appealing choice for applications that prioritize security and transparency. Today, we're going to dive deeper into the fundamentals of blockchain, ensuring that you grasp this exciting technology in a way that feels engaging and digestible. At its core, blockchain technology is a series of nodes working together to form a decentralized network. Imagine a group of friends all playing a game of telephone. Information is passed along, with each person verifying what they hear before repeating it. In the blockchain world, each node has a complete history of the transactions recorded in blocks. When a new transaction is created, it gets added to a block, and then this block has to be validated by the network's nodes. Once validated, the block is added to the chain, creating an unchangeable record of all actions. This decentralized nature is one of the standout features of blockchain. Traditional databases often rely on a central server, meaning if it goes down, so does access to the data. But blockchains, they're like a very tall stack of pancakes spread across a breakfast table, instead of just one big pancake on a solitary plate. If one pancake falls, you still have many more standing strong. Now let's see how we can implement a simple transaction management system in Ethereum using Solidity. In this contract, we have defined an event called transfer that is emitted whenever a transaction occurs. This event includes the addresses of the sender and the receiver, as well as the value being transferred. By indexing both the from and to addresses, we enhance the ability to query past transactions efficiently, making it easier for users to track their transfers. Next, we have the function sendTransaction, which takes two parameters, the recipient's address and the amount to be sent. When this function is called, it triggers the transfer event using the emit keyword, effectively logging the transaction details onto the blockchain. This approach ensures transparency and provides a verifiable record of each transaction executed by the contract. By understanding how to manage basic transactions this way, we lay the groundwork for more complex applications where funds and data can be securely transferred on the blockchain. Once a block is populated with transactions, it's time for all the nodes in the network to agree on its validity through something called a consensus protocol. This can be akin to the old saying, if everyone believes it, then it must be true. In Bitcoin and Ethereum, the proof-of-work method is commonly used. In a nutshell, it requires computational power to solve a complex mathematical problem that validates a block. Think of miners as mathematical puzzle solvers who race against one another to be the first to correctly solve a problem. Once solved, the block is added to the chain, and the first miner to solve the puzzle is rewarded with cryptocurrency, a rewarding strategy for doing mathematics better and faster than your competition. To illustrate, the process looks like this. 1. Nodes receive new transaction data. 2. Nodes pool transactions into a block. 3. Miners solve the cryptographic puzzle. 4. A block is validated and added to the blockchain. 5. All nodes update their copy of the blockchain. This cooperative method prevents malicious actors from easily tampering with the data, as they would need to control over 51% of the network to change historical data, and let's be honest, that sounds like a lot of work. Now let's see how we can compute a hash in Solidity, which is essential for securing blockchain transactions. The code defines a contract named hashExample that includes a function to generate a cryptographic hash. This function, calculateHash, takes a string input and uses the Keccak hashing algorithm to produce a unique output. The ABI encode packed method packages the input string into a single continuous byte sequence, which is then processed by Keccak 256. This ensures that even a slight alteration in the input will yield a completely different hash, highlighting the sensitivity and reliability of cryptographic hashing. The resulting hash is a byte's 32 data type, which means it is a fixed-size array of 32 bytes, making it efficient for storage and quick to reference within the blockchain. By integrating this function into a smart contract, you can ensure that any data integrity can be easily verified, as changes to the input will prompt a different hash, signaling a breach in expected data state and enhancing overall security in transaction processing on the blockchain. Now let's take a look at a fundamental example of a smart contract written in Solidity called Simple Storage. This contract enables users to store a number and retrieve it later, showcasing the core concepts of state management in smart contracts. In this contract, we start by declaring a variable called stored data, which holds the number that we want to save. The set function is publicly accessible, allowing anyone to input a value by passing a number to it. When this function is called, it updates the stored data variable with the new value, effectively setting the data. Next, we have a get function, which is also public but marked as a view function, meaning it does not modify the state of the contract. Instead, it allows users to get the current value of stored data. This two-function setup demonstrates the basic structure of smart contracts where data can be modified and accessed in a controlled way. Through the simple storage contract, we see the potential for automating agreements and managing data without intermediaries, paving the way for more complex contracts in the future. Blockchain technology opened up a world of possibilities that we are only beginning to explore. From decentralized finance, DeFi, to new voting systems, the applications of blockchain and smart contracts are endless. However, with great power comes great responsibility. Because smart contracts are immutable, once deployed, they represent permanent business logic. Code errors or vulnerabilities can lead to severe financial losses. Thus, it's essential to thoroughly test and audit smart contracts before venturing into production. The community is still learning the best practices around security, governance, and scalability. To summarize, the combination of blockchain's inherent security and the potential of smart contracts lays a foundation for a new era of decentralized applications. We all have a part to play in this evolution. Whether you're a developer, entrepreneur, or simply an innovative thinker, embracing these technologies is going to unlock vast opportunities. Blockchain is not just a buzzword, it's a monumental shift in how we think about information, trading, and trust. And as we continue to innovate, the sky's the limit. The journey is just beginning, and it's a fantastic time to dive right in, learn, and explore the blockchain space. So grab your coding caps, stay curious, and let's see where this adventure. Now let's see how we can implement a simple contract to send Ether on the Ethereum network. In this contract, we define a function named sendEther, which takes as parameters the address of the recipient and uses the payable modifier, allowing the function to receive Ether. To ensure that some Ether is actually being sent, we use the require statement to check that MSG value, which represents the amount of Ether sent with the transaction, is greater than 0. This line acts as a guard. If the condition isn't met, the transaction halts with an error message, prompting the user to send some Ether. If the condition passes, we proceed to transfer the Ether to the specified recipient using the transfer method. This method securely sends the specified amount of Ether from the contract to the recipient's address. It's essential to understand that invoking this function constitutes a transaction on the Ethereum network, thereby representing a change in its state. This simple structure encapsulates the process of sending Ether within a smart contract, facilitating direct transfers on the Ethereum platform. Now let's take a look at how we can implement gas management in our Ethereum transaction. In this example, we define a smart contract called gasExample, which contains a function named sendEtherWithGas. This function allows users to send Ether to a specified recipient while ensuring that there's enough gas left to complete the transaction. Here we start by using the require statement to check if there is any Ether being sent. If not, it throws an error with the message, send some Ether. This is crucial because a transaction with 0 Ether serves no purpose. Next, we implement a check using the gasLeft function, which returns the remaining gas before the transaction proceeds. By setting a condition that requires more than 20,000 units of gas left, we help avoid situations where the transaction could fail due to insufficient gas. If this condition isn't met, it will revert with the message, not enough gas. This structured approach to gas management not only ensures successful transaction execution, but also emphasizes the importance of resource planning in smart contract development. Now let's implement the following contract designed to estimate gas costs for transferring Ether, which encapsulates the earlier discussions about gas prices and limits. In this contract, we define a function that takes a recipient's address as an input parameter while making the function payable to allow Ether transfers. First, we capture the current gas price using TX, gas price, which allows us to dynamically assess the cost in GUI during each transaction. Next, we establish a standard gas limit of 21,000 units, which is the typical requirement for transferring Ether. We then calculate the total cost by multiplying the gas price and the gas limit. This gives us the necessary amount of Ether that must be sent along with the transaction to cover both the transfer and gas fees. To ensure that users are providing enough Ether, we use the require statement, which checks that the incoming Ether meets or exceeds the total calculated cost. If this requirement is not met, the transaction reverts, ensuring that the logic of the contract operates smoothly and without unnecessary errors. Finally, if all conditions are satisfied, the recipient is successfully funded with the transferred Ether. Now let's take a look at a smart contract for managing a mutual fund on the Ethereum blockchain. This contract allows users to invest Ether into the fund and withdraw their investments when needed. The invest function enables users to send Ether, ensuring that the investment amount is greater than zero. This function updates the user's balance in the investments mapping, which tracks how much Ether each address has invested in the fund. Next, we will implement the withdraw function, which allows users to withdraw a specified amount from their investments. It includes a safety check to ensure that the user has sufficient funds available, preventing any potential overdraws. Once the conditions are met, the function decreases the user's balance and transfers the specified amount of Ether back to them. This twofold functionality not only allows for investment, but also includes secure withdrawal options. In a dynamic environment where user interactions may increase, managing gas limits becomes crucial for seamless transactions. Therefore, understanding the gas implications of modifying state variables, such as those represented by the investments mapping, is imperative for ensuring the contract operates smoothly. By incorporating these features, we've laid the groundwork for a robust mutual fund management system. Now let's implement the following contract that allows us to specify and control the gas price during a transaction. This code defines a contract called custom gas price, which features an execute transaction function. This function takes in a recipient's address and an amount of Ether to be sent. Inside the function, we first use a require statement to ensure that the amount sent is greater than zero, preventing any transactions with a zero or negative Ether amount. Next, we employ the call method to transfer the specified amount of Ether to the recipient's address, while also specifying a gas limit of 50,000 units. The call method is a lower-level function that provides flexibility over how Ether is sent, allowing us to define the gas amount explicitly. If the transaction fails for any reason, we include another require statement to revert the transaction, ensuring that the Ether transfer does not go through unless all conditions are met. This approach emphasizes the importance of managing gas properly to develop efficient and user-friendly applications on the Ethereum network, fitting seamlessly into our understanding of transaction economics and gas management in decentralized applications. Now let's implement a contract that allows users to deposit and withdraw Ether while incorporating the concept of gas refunds. This contract, named Refundable, starts by establishing a mapping to keep track of user balances. The deposit function allows users to contribute Ether to the contract, updating their balance accordingly. When users wish to withdraw their funds, they call the withdraw function. This function first retrieves the user's balance and verifies that it is greater than zero to prevent any attempts to withdraw without funds. If the condition is satisfied, the contract resets the user's balance to zero to prevent reentrancy attacks, which is a critical security practice in smart contract development. Once this is done, the contract transfers the appropriate amount of Ether back to the user. It's important to note that within this framework, we have a comment that hints at implementing refund logic. This is where we can introduce gas refunds based on previous contract states or reduced gas consumption, potentially offering users a way to reclaim some of their gas costs. This approach not only enhances user experience, but also fosters trust in the smart contract's reliability. In conclusion, understanding Ethereum transactions and gas is crucial for anyone looking to navigate the exciting landscape of decentralized applications. We've covered how transactions work within the Ethereum ecosystem, the importance of gas in facilitating these transactions, methods of estimating gas fees, managing gas limits, and benefiting from gas refunds. By grasping these concepts, you're better equipped to optimize interactions on Ethereum, thus enhancing the experience for both developers and users. Lastly, remember that the world of Ethereum is constantly evolving, and staying up to date with gas fee strategies, transaction execution, and smart contract optimizations will keep you ahead in this dynamic landscape. Thank you for joining today's lesson on Ethereum transactions and gas, and I hope you're now excited to explore further into the vast possibilities of this innovative technology. In today's tutorial, we are diving into the fascinating world of developing smart contracts using Solidity, the programming language that powers Ethereum. This is an exciting topic because smart contracts are what allow decentralized applications to function seamlessly on the blockchain. So far, we learned that Ethereum transactions involve sending Ether and executing functions in smart contracts, gauged by gas, which acts as the fuel for these operations. We explored key elements of transactions, including gas prices, limits, and the essentials of gas management to optimize interactions on the network. Additionally, we discussed how transaction failures impact gas costs and the potential for gas refunds to reduce overall expenses. Now, we will talk about the building blocks of smart contracts and how to effectively develop them using Solidity. Let's kick things off by understanding what a smart contract is. A smart contract is essentially a self-executing contract with the terms of the agreement directly written into code. This means that once the conditions defined in a smart contract are met, the contract automatically executes the necessary actions without the need for intermediaries. Solidity is the language we use to write these contracts, and its syntax is quite similar to JavaScript, making it relatively easy to learn for those already familiar with coding. Let's start our journey by creating our very first smart contract. Now let's explore the implementation of a simple digital wallet using Solidity. This smart contract, named Simple Wallet, employs a mapping to track the Ether balances of each user by associating their address with a corresponding balance value. The deposit function allows users to send Ether to the contract, while the payable modifier ensures that this function can receive funds. It uses the require function to validate that the amount sent is greater than 0, and if so, it updates the user's balance accordingly. Next, we have the withdraw function, which enables users to withdraw Ether from their balance. This function checks that the user has sufficient funds to cover the requested withdrawal amount, again employing the require function for validation. If the conditions are met, the user's balance is decremented, and the specified amount is transferred back to them. This fundamental structure illustrates the core operations commonly found in decentralized applications, emphasizing the importance of condition checks to safeguard wallet operations while allowing users to manage their Ether efficiently. Now let's take a look at how to implement a digital wallet that enforces transaction limits. We start with a contract named Limited Wallet, which contains a mapping for user balances and another mapping to keep track of the last withdrawal time for each user. A constant variable specifies a maximum withdrawal percentage, capped at 10% of the balance. Next, we will implement deposit and withdrawal functions. The deposit function allows users to contribute funds to their balance, ensuring that any deposits must be greater than 0. The withdraw function, on the other hand, checks if the user has sufficient balance and whether their requested withdrawal amount is within the defined limit through the canWithdraw function. This auxiliary function calculates the maximum amount a user can withdraw based on their current balance and the set percentage limit, providing a safeguard against accidental overspending. Through these mechanisms, we ensure that users can efficiently manage their funds while adhering to secure withdrawal practices, creating a safer financial environment within the digital wallet context. Now that we understand how to implement control structures within our smart contracts, let's integrate events to enhance interactions with our contract activities. In this example, we will create the Eventful Wallet contract, which introduces two key events, deposited and withdrawn. These events will log significant activities whenever a user deposits or withdraws Ether from the wallet. Next, we will define the deposit function, which allows users to send Ether to the contract. It ensures that the amount sent is greater than 0 and updates the user's balance accordingly. Upon successful deposit, the deposited event is emitted, providing transparency and real-time updates for front-end interfaces or external applications that track user interactions. Similarly, the withdraw function allows users to withdraw Ether from their balance, adhering to the withdrawal restrictions imposed by the canWithdraw internal function. When a withdrawal occurs, the withdrawn event is emitted, capturing the details of the transaction. This incorporation of events provides an essential monitoring mechanism, improving user engagement and delivering a seamless experience while interacting with the smart contract. Now let's take a look at how we can enhance our smart contract by implementing a modifier to control access. In our code, we've introduced a modifier called onlyOwner, which is designed to ensure that sensitive functions can only be executed by the contract's owner. This is critical for maintaining security and protecting the integrity of our wallet. To achieve this, we declare a state variable, owner, which stores the address of the contract's creator. The onlyOwner modifier checks if the user invoking the function is indeed the owner by verifying that MSG sender matches the owner address. If the caller is not the owner, the transaction will revert with an error message. We leverage this modifier within the withdraw function to enforce strict access control, preventing unauthorized withdrawals. This means that the withdrawal of funds, a sensitive operation, is limited to the contract owner, ensuring that only authorized individuals can perform this critical action. This approach not only cleans up our code by avoiding repetitive checks, but also clearly defines the access rights for different functions, enhancing the overall security of our contract. Now let's take a look at how we can implement a user profile system within our wallet using structs in Solidity. In this contract, we define a user profile struct with two properties: name, which is a string for the user's name, and balance, a uint 256 to represent the user's balance. We use a mapping to associate each Ethereum address with its corresponding user profile, allowing us to store and retrieve profile information efficiently. The create profile function allows users to initialize their profile by providing their name, and it sets their initial balance to 0. This function emits an event, profile created, which logs the user's address and name, making it easier to track profile creation. Next, we have a deposit function that allows users to send Ether to the wallet. Upon depositing, the contract increases the user's balance in two places: the general balances, mapping, and the balance field within their user profile. Finally, the getProfile function returns the user's name and balance. This structured approach enhances the organization and readability of our contract, making it intuitive for users to manage their profiles efficiently. Now let's implement tests for our simple wallet contract to ensure its core functionality works as intended. The test suite begins by importing the simple wallet contract using Truffle's artifacts feature, allowing us to interact with it in our test environment. We set up a contract test suite titled Simple Wallet, which receives the list of accounts available for testing. Next, we will write test cases for two key functionalities: depositing and withdrawing Ether. The first test case checks if a user can successfully deposit Ether into their wallet. We deploy the simple wallet contract, then call the deposit function, sending 1 Ether from the first account. After the transaction, we query the wallet's balance for that account and assert that it equals 1 Ether, which verifies that the deposit was executed correctly. In the second test case, we will check the withdrawal feature. We invoke the withdraw function to allow the user to take out the 1 Ether previously deposited. After executing the withdrawal, we again check the balance associated with the first account, ensuring it is 0 Ether, thus confirming that the withdrawal functionality operates as expected. Regularly running these tests helps to identify unwanted bugs before deploying the smart contract. As we wrap up this exploration of developing smart contracts in Solidity, it's clear that this language provides powerful tools for creating decentralized applications. By building upon fundamental concepts like functions, modifiers, mappings, events, and testing, you can create robust contract environments that not only function effectively, but also provide a better user experience. Remember, the skills you've learned here are just the beginning. The world of decentralized applications is vast and continuously evolving. Constant practice and deeper exploration of Solidity will help you keep up with this dynamic environment. So whether you're enhancing the functionality of your smart contracts or developing the next killer DApp, the possibilities are endless. Thank you for joining me in this tutorial on developing smart contracts, and I can't wait to see what you create. Tokens are an abstraction that represents ownership in the digital world, transforming how we perceive, transfer, and manage assets. In this section, we will delve into token standards that govern ownership, particularly in the context of decentralized applications built on the Ethereum blockchain. So far, we learned about developing smart contracts using Solidity, focusing on their role in enabling decentralized applications on the Ethereum blockchain. We explored Ethereum transactions, gas management, and the creation of a basic digital wallet contract, including transaction limits and access control features. Key concepts such as events and modifiers were introduced to enhance functionality and security, culminating in the importance of testing contracts to ensure reliability. This journey laid the foundation for building complex decentralized applications, encouraging further exploration and practice in Solidity. Now we will talk about token standards, their significance, and how they are implemented using smart contracts. Now let's take a look at a basic implementation of an ERC20 token using Solidity. In this code, we define a smart contract named myToken, which includes essential attributes such as the token's name, symbol, and total supply. The total supply is determined through the constructor, which initializes the balance of the token creator with the total amount specified, adjusted for the token's decimal places. The contract utilizes a mapping to keep track of each address's balance, allowing us to ensure that token transfers are feasible. Next, we implement the transfer function that enables users to send tokens to one another. This function incorporates a require statement to check that the user has enough tokens to transfer, thereby preventing users from going into a negative balance. Once the balance checks out, the tokens are transferred from the sender's account to the recipient's account, and a transfer event is emitted to signal the transaction on the blockchain. This event is crucial for allowing external systems to track token transfers effectively, enhancing transparency and accountability in digital asset transactions. Now let's see how we can implement a simple ERC 721 contract, which is designed for creating non-fungible tokens, or NFTs. The contract begins with the necessary Solidity version declaration and the import statement for the ERC 721 implementation from OpenZeppelin, a well-known library for secure smart contracts. In our contract named myNFT, we define two essential state variables: nextTokenid, which keeps track of the unique identifier for each token, and admin, which stores the address of the contract's creator, responsible for minting new tokens. The constructor initializes the ERC 721 contract with a name and symbol for our NFT collection and sets the admin to the address deploying the contract. Now let's implement the mint function, which is responsible for creating new tokens. It ensures that only the admin can call this function, enhancing security by preventing unauthorized minting. When the function executes successfully, it mints a new token with a unique ID, assigns it to the specified address, and then increments the next tokenid to prepare for the creation of future tokens. This structure is crucial for enabling distinct ownership and trading within the NFT market. Ownership through these token standards fundamentally alters traditional asset ownership. In a conventional setup, transferring ownership often involves intermediaries, lengthy processes, and potential disputes. However, with the introduction of tokens on the blockchain, ownership is simply a matter of sending tokens from one address to another. This efficiency is particularly crucial in sectors like real estate, where transactions can be slow and cumbersome. Consider the implications of these standards in real estate. A property could be tokenized into ERC20 tokens representing fractions of ownership, allowing multiple investors to own a portion of a property. Such a model enhances liquidity and makes investments accessible to a broader audience. The smart contract governing the token would handle transfers, manage ownership records, and possibly even enforce property rules via governance tokens. Now let's see how we can implement security measures in our token smart contract using modifiers. The provided code introduces a modifier called has enough funds, which serves to ensure that the sender has sufficient balance before executing any transfer operations. This is crucial for preventing failed transactions and managing user expectations regarding their token balances. The modifier utilizes the require statement to check if the sender's balance is adequate for the intended transfer amount. If the condition is not met, the transaction will revert, displaying an insufficient balance message. This adds a layer of security by validating transactions at a very basic level. Next, we will write the transfer function, which makes use of the has enough funds modifier. By merely adding has enough funds value to the function signature, we enforce this check transparently. Inside the function, we perform the transfer by deducting the specified amount from the sender's balance and crediting it to the recipient's balance while emitting a transfer event. This event allows external observers, such as wallets and front-end applications, to track token movements efficiently. Through these practices, we've enhanced both the readability and security of our token contract. Now let's take a look at a simple governance token contract that allows users to participate in the decision-making process through voting. This contract uses a mapping to track the votes of each address, where the key is the voter's address and the value is the ID of the proposal they have voted for. The contract includes an important event called voted, which logs the voter's address and the proposal ID whenever a vote is cast. This promotes transparency by keeping a record of who has voted on which proposal. Next, we will implement the vote function, which users will call to cast their ballots. It begins by checking if the user has already voted on a proposal. If they have, the function will throw an error, ensuring that each address can only vote once on any proposal. If they haven't voted yet, their vote will be recorded by updating the mapping with the proposal ID they are voting for. Finally, the voted event is emitted to inform the network about the new vote, reinforcing accountability in the voting process. This contract embodies the principles of decentralization, allowing community engagement in governance decisions. Having explored various token standards, their implementation and functionality, it's important to contextualize their importance in real-world applications. Tokens can streamline processes, reduce costs, and enhance transparency across multiple sectors, allowing individuals to interact with assets like never before. As you continue to explore token standards, keep in mind the importance of continuous learning and adaptation. The blockchain space rapidly evolves, and staying updated with the latest developments will position you well as a developer and innovator. The opportunities are limitless, from opening doors to financial access in developing countries to reshaping how we think about ownership as a whole. To re-emphasize, first we covered the core principles of smart contracts and their relevance in decentralized applications. We explored basic token functionality via the ERC-20 and ERC-721 standards, which serve as cornerstones in the Ethereum ecosystem. These fundamentals empower you to conceptualize and build complex decentralized applications, allowing you to shape the future of ownership and asset management. As we conclude this lesson, take these insights and continue your journey into the exciting world of blockchain technology, where innovation knows no. In this lesson, we will explore the exciting application of blockchain technology in supply chain management. Blockchain has the potential to revolutionize the way products move from suppliers to customers by enhancing transparency, security, and efficiency in the supply chain. So far, we covered the fundamentals of tokens as representations of ownership in the digital world, focusing on token standards like ERC-20 and ERC-721. Now, we will delve into how blockchain can transform traditional supply chain practices and examine its practical implementations. The essence of a supply chain encompasses the organizations, people, and processes involved in moving products from suppliers to customers. Traditionally, this intricate network has faced numerous challenges, including a lack of transparency, inefficiencies in tracking and managing products, and difficulties in ensuring accountability along the way. However, integrating blockchain technology offers innovative solutions to these long-standing issues, enabling a more resilient and efficient supply chain. Now let's implement a smart contract that facilitates managing products within a supply chain using blockchain technology. This contract defines a product structure that contains vital details about each product, such as its unique ID, name, origin, and the current owner's address. These details are crucial for maintaining transparency and traceability in the supply chain. Next, we introduce a mapping called products, which allows us to store each product using its ID as a key, making it publicly accessible for querying. The add product function empowers suppliers to register new products by providing their ID, name, and origin. When a product is added, the contract creates a new product instance, assigning the sender's address as the initial owner. Furthermore, the transfer ownership function enables the current owner to transfer ownership to another address. It ensures that only the product's owner can execute this function, reinforcing accountability. By keeping a permanent record of each product's ownership and journey from farm to table, this contract exemplifies how blockchain technology can transform supply chain operations, enhancing trust and ensuring accurate tracking. Next, we will write a smart contract called Checkpoint Supply Chain, designed to improve product tracking within a supply chain by utilizing checkpoints. In this contract, we define a checkpoint structure that holds the location and timestamp of a product as it moves through different points in the supply chain. This allows us to create a detailed record of where a product has been and when it reached each checkpoint, enhancing traceability. We also introduce a product struct that consists of an ID, name, and an array of checkpoints. This setup allows each product to have its own unique set of location data, creating a comprehensive history for anyone who needs to reference it. The mapping products stores all products associated with their IDs, making it easy to access individual product details. Now let's see how we can implement the add checkpoint function. This function enables users to add a new checkpoint for a specific product by providing its ID and location. Whenever a new checkpoint is added, the current timestamp is recorded, ensuring a verified trail of the product's journey. Lastly, we have the getProductInfo function, which allows users to retrieve essential information about a product, including its checkpoints, fostering an environment of accountability and reliability in the supply chain. Now let's take a look at the smart contract designed for integrating IoT data into supply chain management. This contract, named IoT Checkpoint Supply Chain, provides a framework for managing products with a focus on quality data obtained from IoT sensors. The product structure contains essential attributes such as ID, name, quality data, and owner, allowing for comprehensive tracking of each product's status and quality. Next, we define a mapping called products to store all products in the system. The add product function enables the addition of new products to the blockchain, with the product's ID and name being specified by the user, while the owner is set to the address of the person who creates the product entry. This establishes clear ownership right from the start. Importantly, the update quality data function allows only the product owner to modify the quality data field. This feature ensures that sensitive quality information, potentially captured by IoT devices, is secure and accurately reported. By integrating such functionalities, the contract enhances traceability, accountability, and reliability within the supply chain operations. Now let's talk about the potential challenges that come with implementing blockchain in supply chains. One of the main concerns is the integration of existing systems with blockchain technology. Many organizations have legacy systems that may not be easily compatible with blockchain solutions. It's crucial to assess the technical feasibility and prepare for potential migration processes. Another challenge lies in user adoption. Stakeholders across the supply chain need to understand how to use the technology and its benefits. Training and demonstrating practical applications can help ease the transition into a blockchain-enabled system. A smooth user experience is imperative for the success of any new technological integration, particularly in an environment that requires synchronization among multiple parties. Security is another significant aspect to consider. While blockchain is designed to be secure, vulnerabilities such as 51% attacks and inadequate coding can pose threats. Therefore, thorough testing and validation of smart contracts are essential. To wrap everything up, the application of blockchain technology in supply chain management holds tremendous promise. It enhances transparency, traceability, and accountability, resulting in a more efficient and reliable process from suppliers to customers. Through smart contracts, product tracking, and IoT integration, organizations can streamline operations and significantly reduce fraud and inefficiencies. As we move further along in exploring blockchain applications, it's crucial to understand how these technologies can be tailored to meet the specific needs of various industries. Continuous learning and experimentation in blockchain solutions can lead to innovative practices that redefine sectors globally. The future of supply chains is on the horizon, and blockchain technology is a significant part of it. So far, we have learned about a wide range of applications in blockchain, from token management to more complex systems like supply chains, setting the stage for further exploration into how technology can reshape traditional processes and address modern challenges. Now, let's open the floor for questions and discussions about the fascinating world. When you own a long-term asset, such as a house or a car, proper maintenance is crucial to ensuring that the asset retains its value over time. The idea of maintaining a log to track every service or repair conducted on these assets is not just a good practice. It can significantly affect their overall resale value. Permanent records of maintenance actions can provide insights into the asset's condition, assisting in future repairs and helping prospective buyers feel confident in their purchase. So far, we've learned about the transformative potential of blockchain technology in supply chain management, highlighting its ability to enhance transparency, efficiency, and security. We explored how smart contracts can facilitate product tracking, accountability, and the integration of IoT for improved quality monitoring. Additionally, we addressed the challenges of implementing blockchain, including system compatibility, user adoption, and security concerns. This foundation sets the stage for further investigation into blockchain applications across various industries. Now, we will cover the significance of permanent records, particularly in the context of asset management, and how blockchain technology can provide a reliable solution for maintaining these records. Now let's take a look at how we can implement a smart contract to maintain maintenance records for assets, specifically utilizing Solidity. The asset maintenance contract begins by defining a structure for each maintenance record, which includes an identifier, a description of the service performed, and a timestamp for when it occurred. This structured approach ensures that all relevant details about each maintenance action are captured systematically. Next, we maintain a mapping that links user addresses to their respective arrays of maintenance records, allowing multiple entries per user. The Add Maintenance Record function enables users to create new records by providing a description. It automatically assigns an ID based on the current number of records stored. This functionality not only captures the user's input, but also timestamps the record with the current block's timestamp, making it easy to track the chronology of maintenance actions. Finally, users can view their maintenance logs through the getMaintenanceRecords function, which returns the array of records associated with the address calling it. By utilizing blockchain technology, this setup guarantees that the records are tamper-proof and accessible, ensuring reliability in maintaining asset histories. Now let's implement the following smart contract to manage maintenance records specifically for properties. In this property maintenance contract, we start by defining two structures: maintenance record, which holds details about each maintenance activity including an ID, description, and date, and property, which links a property address to its associated maintenance logs. Next, we declare a mapping from addresses to individual properties, enabling each user to register and maintain records for their own properties. The register property function allows users to register a new property by providing the address, effectively initializing a new property entry with an empty array for maintenance logs. To add maintenance records, the addMaintenanceRecord function is introduced. This function creates a new maintenance record for the user's property, automatically incrementing the ID based on the current number of logs linked to that property. The record captures the description of the work done and the timestamp of when it occurred, ensuring that all entries are timely and well documented. Finally, the getMaintenanceRecords function allows users to fetch all maintenance logs pertaining to their registered property, promoting transparency and accessibility. This contract exemplifies how blockchain can facilitate permanent record keeping, enhancing accountability and trust in property management. Now let's implement a smart contract that focuses on managing maintenance histories for industrial equipment. We start by defining the maintenance record struct, which will store essential details such as an ID, a description of the maintenance performed, the date of the maintenance, and the equipment ID associated with the record. This structure helps us keep a detailed log of maintenance actions tied to specific equipment. Next, we create another struct called equipment, which contains the equipment's name and an array of maintenance logs. This setup allows us to associate multiple maintenance records with each piece of equipment effectively. We achieve this through a mapping that links a unique equipment ID to its corresponding equipment instance. To register a piece of equipment, we define the registerEquipment function, which takes an ID and a name as inputs. Upon invocation, it initializes a new equipment entry in the mapping. Following that, the addMaintenanceRecord function enables users to add maintenance records specific to the equipment by providing an ID and a description. Finally, to retrieve the maintenance history of a piece of equipment, we implement the getMaintenanceRecords function, allowing users to access the logs associated with any equipment ID. This structure significantly enhances compliance and safety within industrial settings. Now let's take a look at a Solidity smart contract designed for analyzing maintenance records related to equipment management. This contract defines a structure for maintenance record, which captures the unique ID, a description of the maintenance action, and the date when it occurred. We also define an equipment structure, which contains the name of the equipment and an array of maintenance logs associated with it. To register new equipment, the registerEquipment function is implemented, storing the name and initializing an empty array for maintenance logs. This sets the foundation for tracking maintenance actions over time. Next, we introduce the addMaintenanceRecord function, which allows users to log maintenance activities by creating a new maintenance record each time it is called. This function assigns a unique ID based on the current length of the maintenance logs and records the action's details alongside the current timestamp. Finally, the contract provides a getTotalRecords function, enabling users to retrieve the total number of maintenance actions performed on a particular piece of equipment. This straightforward metric can lead to insightful analysis when considered alongside historical data, ultimately enhancing decision-making within an organization. The immutability of blockchain creates a reliable foundation for all these applications. Once data is recorded, it cannot be modified or deleted, ensuring that records maintain their integrity over time. This quality can be beneficial for audits, where having an accurate log of events or transactions plays a crucial role in compliance checks. Auditors can easily verify maintenance logs linked to a manufacturing process, various equipment, or assets in real time without risking data tampering. Moreover, having permanent and transparent records allows for trust within organizations and their stakeholders. For industries like healthcare and finance, where transparency and accountability are pivotal, permanent records can provide peace of mind about compliance and ethical standards. By empowering individuals and organizations with reliable data, we can foster a more trustworthy business environment. In conclusion, permanent records hold immense importance across various industries, fundamentally changing how we view asset management. The ability to track and verify maintenance actions can improve the asset's value, ensure compliance, and facilitate informed decisions. Blockchain technology provides an innovative way to secure these records, making them immutable and transparent. As we delve deeper into the applications of blockchain, the potential to reshape industries by harnessing the power of permanent records becomes ever clearer. Whether you're managing personal assets, leading a company, or operating in regulated sectors, the significance of maintaining transparent, reliable records cannot be overstated. In this session, we will dive into setting up tools for smart contract development. This is an essential step for anyone looking to bring their blockchain ideas to life. From coding your first contract in Solidity to deploying it on the blockchain, the right tools will make this journey smoother and more efficient. So far, we learned about the importance of maintaining permanent records for long-term assets, emphasizing how they enhance overall value and buyer confidence. We explored blockchain technology as a solution for securely storing these records, ensuring transparency and immutability. Additionally, we discussed how permanent records support compliance across industries and enable proactive maintenance strategies. This foundation highlights the transformative potential of transparent data management in asset management and decision-making. Now, we will explore the necessary tools for smart contract development, equipping you with the skills and knowledge to effectively create and deploy your own smart contracts. Now, let's take a look at a simple Solidity smart contract called Simple Token. This contract is designed to represent a basic fungible token with a specified name, symbol, and total supply. The first line specifies the Solidity version, which is essential for ensuring compatibility with the features and syntax used in the contract. Next, we define the Simple Token contract. It declares three public state variables: name, symbol, and total supply. The name variable assigns the token a recognizable title, Simple Token, while the symbol provides its shorthand representation, SDK. Importantly, total supply is set to 1,000, denoting the total number of tokens available. We also establish a mapping called balance of, which enables tracking the token balance of each address within the Ethereum network. Finally, the contract includes a constructor that automatically assigns the total supply of tokens to the account deploying the contract, which is indicated by MSG, sender. This constructor ensures that the creator of the token starts with the total supply in their balance, setting the foundation for future transactions and token distribution. Now let's explore how to set up Truffle in our environment. First, we need to install Truffle globally on our system using npm, which allows us to run the Truffle command from any directory. By running the command, we ensure that we can create and manage multiple projects effortlessly. After the installation, the next step is to initialize a new Truffle project. This can be accomplished by navigating to the desired directory and executing the initialization command. This command creates a dedicated workspace for our project, establishing essential directories like contracts, migrations, and test. The contracts directory is where we'll place our Solidity files, while the migrations directory holds deployment scripts necessary to deploy our contracts onto the blockchain. The test directory will serve our unit tests, making verification of our smart contracts more manageable. This structured setup not only organizes our code effectively, but also promotes best practices in smart contract development. Thus, as you proceed, you'll have a solid foundation for building and deploying your projects seamlessly. Now let's see how we can implement our testing strategy for the Simple Token smart contract using Truffle's JavaScript testing framework. We begin by requiring the Simple Token contract artifact, which allows us to interact with the deployed version of the contract. Next, we define a test suite for the Simple Token contract, utilizing the contract function provided by Truffle, which facilitates grouping our tests together. Within this suite, we'll create an individual test case using the it function, where we will verify that the first account received the total supply of tokens. Here, we will asynchronously fetch the deployed instance of the Simple Token contract, ensuring that we are working with the latest version deployed on the blockchain. Utilizing the balance of function, we will check the balance of the first account, which should be equal to 1,000 tokens. Finally, we will use the assert_equal method to compare the retrieved balance with the expected value. This check ensures that our smart contract properly allocates the total supply to the designated user upon deployment, showcasing the fundamental logic behind token distribution. By running these tests, we can confirm the expected behavior of the contract before it goes live. Now let's take a look at how we configure our Truffle project for deployment to Ganache. To begin, we need to set up the Truffle config.js file, which handles the network settings for our project. In this configuration, we utilize HD Wallet Provider, which allows us to securely manage our wallet and connect to the Ethereum network through Infura. You'll need to replace placeholders like YOUI and FURA key and your mnemonic with your actual Infura key and your wallet's mnemonic phrase, respectively. Next, we define the development network settings, specifying our local Ganache instance with the appropriate host and part number. This setup ensures that Truffle can communicate with Ganache to deploy contracts locally. Additionally, we include the Solidity compiler configuration to specify the required version of Solidity that we want to use for compiling our contracts. Now that our configuration is set, let's write the migration script. This script tells Truffle how to deploy our smart contracts. We will include the simple token contract in the migration script, allowing Truffle to handle the deployment process easily. With this in place, we can then execute Truffle Migrate Network Development to deploy our contracts to the Ganache blockchain and see confirmation in the terminal of a successful deployment. Now let's take a look at how we can interact with our deployed smart contracts using Truffle's console. First, we'll enter the console by running a command that connects it to our development network. This console acts as a command line interface, allowing us to execute various commands and interact seamlessly with our deployed contracts. Once inside the console, we can create an instance of the simple token contract, which represents our token, and then check the balance of the first account. This is accomplished by calling the deployed function, which returns a promise that resolves to our contract instance. From there, we can use the balanceOfCall method to query the balance of a specific account, in this case, accounts. This will provide us with the amount of simple token held by the first account. After executing this code snippet, we should see the balance printed on the console. This process not only demonstrates how to retrieve and display information from our contract, but also highlights the interaction capabilities offered by Truffle, making it easier to work with our smart contracts and ensuring we can verify their state directly post-deployment. In summary, we have covered the essential tools for effective smart contract development, including VS Code and its Solidity extension for efficient coding, Truffle as a comprehensive framework for development and testing, and Ganache for deploying and testing your contracts on a local blockchain. With these tools, you are well equipped to develop, test, and deploy your smart contracts efficiently. Keep practicing, and you'll soon be building your decentralized application. To engage users in the world of Ethereum, an efficient and user-friendly wallet is crucial. Today, we'll cover how to install and configure Metamask, a popular browser extension that serves as a wallet for your Ethereum assets. It's important to note that if your application requires users to download and run a full Ethereum client such as Parity or Geth, you just lost a lot of potential users. With Metamask, not only can you manage your Ether and tokens effortlessly, but you can also interact with decentralized applications right from your browser. In this lesson, we will dive deep into the installation and configuration process of Metamask, including tips, tricks, and code examples for a smoother experience. So far, we learned about the essential tools for smart contract development, including the significance of coding environments like Visual Studio Code and the Solidity extension to enhance productivity. We also introduced Truffle as a robust framework for managing the smart contract lifecycle and discussed the importance of testing with JavaScript to ensure functionality. Additionally, we covered how to deploy contracts using Truffle in conjunction with Ganache to create a local Ethereum blockchain. These foundations equip you with the skills needed to effectively develop, test, and deploy your own smart contracts. Now, we'll talk about Metamask and how it acts as a bridge to the world of Ethereum. Let's start with the installation process of Metamask. The great thing about Metamask is that it's available as a browser extension for popular web browsers like Chrome, Firefox, and Brave. To get started, open your preferred web browser and head over to the official Metamask website at Metamask.io. This is crucial. Always download from the official site to prevent phishing scams or malicious software. Once you're on the website, click on the Download button. It will guide you to select the appropriate extension for your browser. If you're using Chrome, you'll be redirected to the Chrome Web Store. Click on Add to Chrome, and in a few moments, the extension will be part of your browser's toolbar. After installation, look for the Metamask icon. It typically resembles a fox's head and is located in the top right corner of your browser. Click on the icon and a welcome screen will greet you. You might be wondering how long this setup will take. Spoiler alert, it won't take long at all, so let's get right into it. Now that you have Metamask installed, let's set it up. You will see an option to get started. Click it, and you will be prompted to create a new wallet or import an existing wallet. If you're new to the world of Ethereum, creating a new wallet is likely the way to go. So click on Create a Wallet. You will be asked if you want to help improve Metamask by allowing anonymous usage data to be collected. This is a personal choice. After making your selection, set a strong password for your wallet. This will be crucial for accessing your wallet in the future. Make sure it's not something easy to guess and jot it down somewhere secure. Keep in mind that this password is for local access and doesn't protect your wallet from external threats. Now, this is where it gets serious. Metamask will generate a secret backup phrase, also known as a seed phrase. This is a 12-word phrase unique to your wallet, and it is the key to retrieving your wallet if you ever lose access. Metamask will display your backup phrase, and it's crucial to write it down or store it safely offline. This phrase can't be recovered if lost, so treat it like the treasure it is. The moment you confirm that you've written it down, you will be required to re-enter the seed phrase in the correct order. This ensures you've recorded it correctly. Once that's done, congratulations. You now have your own Ethereum wallet set up. But we are not done yet because we need to connect our wallet to the Ethereum mainnet or a test network, depending on your purpose. By default, Metamask connects to the Ethereum mainnet, but for development purposes, using a test network can save you real money on transaction fees. To change networks, look for a drop-down at the top of the Metamask interface. Click it and select a test network like Ropsten or Rinkeby. These networks simulate the Ethereum environment but use Test Ether, which is free and can be obtained from a faucet. Great, you've nearly completed the initial setup. Now it's time to add some Ether to your wallet, particularly if you want to experiment with transactions. For that, you can use a test network faucet such as the Ropsten Ethereum faucet. Navigate to a faucet website, and you will likely need to provide your wallet address to receive free test Ether. Don't worry, this process is straightforward. To find your wallet address, click your account icon at the top right corner of Metamask. You will see your account name and the wallet address. Copy this address to your clipboard. Go back to the faucet site and paste your wallet address there. Follow any additional instructions, and soon enough, you will see your test Ether reflecting in your Metamask wallet. Now let's explore Metamask's interface further. Here's where the magic happens. You are greeted with a clean and user-friendly interface that shows your wallet balance, transaction history, and more. You can also manage multiple accounts within Metamask, allowing you to separate funds for different projects or purposes easily. To create additional accounts, click on your account icon and select Create Account. Enter a name for your new account, and voila. You have another account ready to use. One of the most exciting features of Metamask is the ability to interact with decentralized applications, DApps. DApps are platforms that utilize blockchain technology, and Metamask acts as a bridge, allowing you to connect seamlessly. For example, let's say you want to buy tokens on a decentralized exchange like Uniswap. First, visit the Uniswap website. If this is your first time using it, connect your Metamask wallet to the DApp by clicking on the Connect Wallet button. Metamask will prompt you to select which account you'd like to connect. Choose the desired account, and it will establish a connection. There you have it. You can now swap tokens or provide liquidity directly through your wallet. Let's take a closer look at transactions. When you execute a transaction like swapping tokens, Metamask will open a confirmation screen. Here, you will see the transaction details, including gas fees. Gas fees are the charges for performing transactions on the Ethereum network. Make sure to review them before confirming, as they can vary significantly based on network congestion. You can also adjust the gas limit and gas price if you wish to speed up your transaction, but always be cautious. Higher fees mean you'll be spending more for the same transaction. After confirming, you'll see a loading screen, indicating the transaction is pending. Once it's completed, you can view the details on Etherscan, a block explorer that provides you with insights into Ethereum transactions. Once you gain confidence using Metamask, you might want to explore its settings. Click on your account icon and navigate to the settings option. Here, you'll find various options like security preferences, network settings, and token management. You can enable the Show Hex Data option if you are sending tokens. This will show you the raw transaction data, which can be instructive as you advance in your Ethereum understanding. To further enhance your experience with Metamask, consider adding custom tokens. Let's say you receive some tokens on a new protocol or from an ICO that isn't automatically recognized by Metamask. No worries, you can manually add them. First, navigate to the Assets tab and scroll down to Import Tokens. On this page, you can enter the token contract address, which you can usually find on the project's website or from the Ethereum Blockchain Explorer. Once you enter the contract address, Metamask will automatically fetch the token symbol and decimals. After you complete this step, your new token will appear in your wallet alongside your Ether. And remember, Metamask is constantly evolving, with features like hardware wallet support for added security. If you're someone who holds significant value in your wallet, investing in a hardware wallet can be wise. It adds an extra layer of security by keeping your private keys offline. Don't forget the importance of security. Metamask has built-in measures, but users must also exercise caution. Always double-check URLs before entering your seed phrase or wallet details. Phishing attacks are prevalent in the crypto world, and malicious actors use tricks to steal your assets. For an added layer of protection, consider enabling two-factor authentication wherever possible. While MetaMask itself doesn't support 2FA, your email and other associated accounts should absolutely have this feature enabled. Finally, periodically review your MetaMask account for unauthorized transactions. Regularly checking your transaction history ensures you spot any unusual activity early. If you ever suspect your wallet has been compromised, change your password immediately and consider resetting your seed phrase. However, if your seed phrase is compromised, you need to move your assets to a new wallet urgently. In conclusion, installing and configuring MetaMask is straightforward and opens a world of possibilities in accessing Ethereum and its decentralized applications. With your newly installed wallet, you can easily manage tokens, swap assets, and engage with dApps while keeping your funds secure. Embrace the journey of Web3 and decentralized finance, but always remember the importance of security and vigilance in the crypto space. With these insights, you are now prepared to navigate Ethereum and participate in its growing ecosystem confidently. From MetaMask to managing your digital assets, the power is now in your hands to explore, interact, and innovate in the decentralized world. So let's dive into the future together, one block. In this video, we're diving into the exciting world of decentralized applications, or dApps, using the Truffle toolset and the Solidity programming language. Building a simple dApp is not just a great way to get a hands-on experience with blockchain technology. It's also a classic way to showcase what you've learned about Ethereum, smart contracts, and wallets. So far, we've covered the importance of having a user-friendly wallet in the Ethereum ecosystem and how to effectively manage your assets through MetaMask. Now, let's create a basic dApp that will enable us to explore the Truffle framework and the capabilities of Solidity. Now let's confirm that Node.js is properly installed on your machine. To do this, open your terminal and enter the command to check the Node.js version. This step is crucial because it ensures that your development environment is set up correctly. If the command executes successfully and you see a version number, you can confidently proceed to the next phase of our project. Next, we will install Truffle, a powerful framework that simplifies the process of writing and deploying smart contracts. By typing in the installation command, you will add Truffle globally to your system, making it accessible for all your projects. Once the installation is complete, you can verify it by checking the Truffle version in your terminal. This ensures you have the right version set up and ready for development, allowing you to leverage the features that Truffle provides for building decentralized applications. With these installations confirmed, we can now confidently move forward to create our very own dApp. Now let's implement the commands to create our project directory and initialize our Truffle project. First, we will use the command mkdir-simple-dApp to make a new folder named simple-dApp, which will serve as the home for our decentralized application. After creating the folder, we navigate into it with cd simple-dApp, ensuring that our terminal is directed to the right location. Next, we'll initialize a Truffle project by typing truffle init. This command is crucial as it sets up the foundational structure for our dApp. When executed, Truffle will generate several essential files and directories, including a contracts folder, which is where we'll store our smart contracts, a migrations folder to manage the deployment process, and a test folder for any testing requirements we may need later. This structured setup allows us to keep everything organized, focusing our efforts on developing the functionality of our dApp without getting lost in a disordered directory. Having this structure in place is a significant step toward building our first smart contract. Now let's implement the following code for our simple storage smart contract. The first line sets the SPDX license identifier as MIT, which helps clarify licensing terms for developers interacting with our code. We then specify the Solidity compiler version in the Pragma directive, ensuring compatibility during compilation. Next, we declare our simple storage contract. Inside this contract, we create a single state variable named stored data of type uint, which signifies that it can only hold non-negative integers. Now let's see how we can add functionality. We define a set function that takes an unsigned integer as input, allowing users to store a new value in stored data. This function is marked as public, making it accessible from outside the contract. Moving on, we add a get function that returns the current value of stored data. This function is tagged as public view, indicating that it does not change the contract state and can be called by anyone at any time. This simple yet powerful setup provides a clear understanding of how to interact with data on the blockchain, forming a fundamental building block for more complex decentralized applications. Now that we have our smart contract written, it's time to set up the migration file, which is crucial for deploying our contract to the Ethereum network via Truffle. Next, we will write a JavaScript file named toDeployContracts.js inside the migrations directory. In this file, we begin by importing our simple storage contract using Truffle's artifacts_require method, which allows us to reference the compiled version of our smart contract. Now let's implement the deployment process using the deployer object that Truffle provides. This object gives us the ability to deploy our contract to the blockchain. The deployer_deploy method takes the simple storage contract as its argument, instructing Truffle to handle the deployment process. This neat encapsulation simplifies deploying contracts, as we don't have to manually specify deployment parameters or interact with the blockchain directly. Truffle takes care of that for us. Once our migration script is complete, we can initiate the deployment process from the terminal with the command truffle migrate. This command compiles the smart contract and migrates it to the local blockchain, set up by Ganache, which we'll use for development and testing purposes. After successful deployment, Truffle will output the address of the deployed contract, indicating that everything is set up and ready for interaction. Now that we have our smart contract deployed, let's put it to the test within the Truffle environment. First, we'll start the Truffle console, which provides an interactive JavaScript environment for interacting with our deployed contracts. We do this by typing Truffle console in the terminal. Next, we'll retrieve the deployed contract instance. This allows us to interact with our simple storage contract, so we execute the command to get a reference to the deployed instance. Once we have the instance, we can set a value in our contract. Specifically, we use the set function to store the number 123. This function is designed to update the state variable in our smart contract. Following that, if we want to retrieve the stored number, we call the get function on our contract instance. This function fetches the current value of our stored data. Finally, to see the result in the console, we log the retrieved value, converting it to a string for proper display. After running these commands, you should see 123 printed out, a satisfying confirmation that our DApp is working correctly. Now let's take a look at how we can implement the front end of our DApp using HTML. We will create a basic HTML structure that serves as the user interface for our simple storage DApp. The document begins with a declaration and specifies the language for accessibility. Inside the head section, we set the character encoding and viewport settings to ensure responsive design across devices. We include a title for the web page and link the Web3 library via CDN, which is vital for interacting with our Ethereum smart contract. Additionally, we defer loading our custom JavaScript file, app.js, until after the HTML is paused. In the body of the HTML, we define an engaging header that welcomes users to the simple storage DApp. We then provide an input field allowing users to enter a number they wish to store on the blockchain. Two buttons are included, one to set the value in our smart contract and another to retrieve it. Finally, we establish a paragraph element to display the result fetched from the contract. This simple yet effective interface will facilitate seamless interaction with the underlying smart contract functions, promoting ease of use for users engaging with our DApp. Now let's implement the necessary front-end logic in our app.js file, which will enable interaction between our smart contract and the user interface of our DApp. First, we define an asynchronous function called init that checks for the presence of Metamask in the user's browser. If Metamask is installed, we initialize Web3 to enable communication with the Ethereum network and invoke the startup function. However, if it is not installed, we alert the user to install Metamask to proceed. Next, we set up the startup function, where we specify the contract's address and ABI. These details are essential for our application to know which smart contract to interact with. We create a new instance of the smart contract using these values. Then we add event listeners to the buttons in our HTML file. The set value button retrieves the input value, fetches the user's Ethereum accounts, and sends a transaction to set that value in the smart contract. Meanwhile, the getValue button calls the smart contracts method to fetch the stored value and updates the displayed result. This setup allows users to seamlessly interact with the blockchain through the DApp interface. Now let's implement the following commands to serve our DApp locally. The first command installs the HTTP server package globally on your machine. This is a simple way to create a local server, which is especially useful for static files like those in your client folder. Once HTTP server is installed, the second command allows you to serve the contents of the client folder. By doing this, you're setting up a local server environment that will host your DApp, making it accessible via a web browser. After running these commands, you will receive a URL printed in the terminal. This URL is where you can view your DApp interface. It is crucial that you navigate to this URL in your browser to interact with your application. You should see the user-friendly interface we designed, where you can enter a number and interact with your smart contract. This setup will let you test the functionality of your DApp and ensure it communicates correctly with the deployed smart contract on the local blockchain. Once your DApp is displayed, try entering a number and setting it. After you set a value, use the Get Value button to retrieve it, and you should see your entered number displayed below. Like magic, right? You've successfully created a simple decentralized application. Throughout this tutorial, we've covered the essentials: setting up Truffle, writing a smart contract in Solidity, deploying it with migrations, and building a user interface to interact with it. To wrap things up, building a basic DApp is an empowering experience. Not only have you dipped your toes into solitary programming and learned the workings of the Truffle framework, but you've also gained practical skills in connecting blockchain applications with user-friendly interfaces. From smart contracts to front-end interactions, you've seen how DApps operate. The potential of decentralized applications is boundless, and you are now armed with the knowledge to go forth and create even more complex applications. As you continue to explore the world of Ethereum, remember that the community is always growing, and there are numerous resources available to aid your journey. Keep coding, keep experimenting, and enjoy the ride into the world of decentralization. In this lesson, we are going to dive into the exciting world of smart contracts by building a Greta contract using Truffle. Smart contracts are a fundamental component of decentralized applications, allowing for trustless interactions between parties. Get ready as we expand our knowledge and skills in developing DApps that can greet users in a fun and engaging way. Now let's take a look at the basic structure of our Greta contract implemented in Solidity. Here, we declare a contract named Greta, which will serve as our simple interface for greeting users. Within this contract, we introduce a public string variable called greeting, which will hold the message we want to display. By declaring it as public, Solidity automatically generates a getter function, allowing users to easily access the current greeting message from the front end. Next, we implement a constructor for our Greta contract that takes a string argument, greeting. This constructor initializes our greeting variable with the value provided when deploying the contract. This setup is essential as it ensures that users are greeted with a personalized message right from the start. With these elements in place, we have laid the foundation of our Greta contract, enabling straightforward retrieval and storage of user greetings, which we can further enhance in the next steps of our tutorial. Next, we will implement a function that allows users to update the greeting message in our Greta contract. This is achieved with the setGreeting function, which takes a string input called greeting. By marking this function as public, we ensure that it can be called from outside the contract, enabling user interaction. This is an important feature because it adds flexibility, allowing anyone to customize the greeting message after the contract has been deployed. In the body of the function, we assign the input greeting to the greeting state variable. This action updates the stored greeting message with whatever the user inputs. This dynamic capability transforms our Greta contract from a static entity into an interactive application, whereby users can personalize their experience. As we build DApps, incorporating user-modifiable elements like this fosters engagement and enhances functionality, showcasing the practical relevance of smart contracts in decentralized applications. Now that we have our Greta contract set up, it's time to deploy it on a local blockchain using Truffle. First, we will initialize a new Truffle project by executing the command truffle init in the terminal. This command will create a new directory structure for our project, including essential folders like contracts, migrations, and test, which will help us organize our code and files effectively. Next, we will create a migration script that facilitates the deployment of our Greta contract. In the migrations directory, we will create a file named toDeployGreta.js. In this script, we start by importing our Greta contract using artifacts require Greta. This line allows us to interact with the compiled contract. We then define a module that exports a function where we instruct Truffle to deploy the contract. The deployer deploy Greta hello world. Line is crucial. It deploys the Greta contract to the blockchain with an initial greeting message of hello world. This deployment script plays a key role in managing how a smart contract is rolled out, ensuring it is set up correctly on the local blockchain for further interaction. Now that Ganache is running and we have our migration script ready, we can deploy our Greta contract using the truffle migrate command. This command compiles the Solidity contracts and executes the migration scripts, which in our case include the deployment of the Greta contract initialized with the greeting message, hello world. If everything is set up correctly, you will see confirmation in the terminal indicating a successful deployment. Next, we will interact with our deployed contract through the Truffle console, which provides a convenient way to execute commands against our smart contracts. By entering Truffle console, we enter an interactive environment where we can query blockchain data and manipulate our contract states. Now let's take a look at how we can retrieve the current greeting message stored in our greeter contract. We will first create a variable to hold an instance of our deployed contract, then call the greeting function to fetch the message. The console will output "Hello, world," if all works as intended, confirming the contract's functionality and readiness for user interaction. Now that we've confirmed our greeter contract is functional, let's test out the setGreeting function. To modify the greeting message, we will execute a command in the Truffle console, calling greeter instance, setGreeting, welcome to the blockchain world. This command allows us to update the state of our smart contract by passing a new string that will replace the current greeting message. Once we do this, we need to ensure that the change has been successfully applied. Next, we will retrieve the updated greeting by executing greeter instance, greeting, then new greeting equals console log new greeting. This utilizes the promise-based nature of JavaScript to fetch the current greeting stored in the contract after the update. By invoking this function, we can verify whether the greeting has indeed changed. If everything works correctly, we should see "Welcome to the blockchain world" output in the console instead of the initial "Hello, world." This interactive capability of smart contracts exemplifies how decentralized applications enable direct interaction with the contract state, enhancing user engagement and experience. Now let's take a look at how we can create the front-end interface for our greeter decentralized application, DApp, using HTML and JavaScript. First, we define the document type and set the language attribute to English in the HTML structure. Next, we include meta tags to ensure proper character encoding and responsive design on various devices. The title of our page is set to Greeter DApp, which will appear in the Browser tab. In the body of the document, we create a simple layout that includes an H1 header indicating the title of our DApp. We then insert a div that contains an H2 element, which will display the current greeting fetched from our smart contract. Below it, we provide an input field where users can enter a new greeting message and a button that will trigger the action to update the greeting. Lastly, we link a JavaScript file named app.js. This structure forms the foundation of our interface, allowing users to interact with the greeter contract seamlessly, facilitating a user-friendly experience as they submit and modify greeting messages without refresh. Now let's implement the following JavaScript code to enhance our greeter DApp, allowing it to interact seamlessly with the Ethereum blockchain. We start by listening for the window load event, ensuring all elements are fully rendered before running our script. First, we check if the user has a Web3 provider like Metamask. If not, we alert them to install it, as it's essential for interacting with Ethereum. Next, we define the address of our deployed greeter contract and its ABI, a crucial element that allows us to communicate with it. We then create an instance of the contract using Web3.js, setting the stage for our DApp's functionality. The updateGreeting function retrieves the current greeting from the smart contract through a method call, updating the displayed greeting in the HTML accordingly. Finally, we handle user interactions. When the user clicks the button to set a new greeting, the new greeting input value is captured, and the setGreeting function is invoked. This function sends the updated greeting to the smart contract using the user's Ethereum account, and afterward, we call updateGreeting again to reflect the change in the interface. This interaction showcases the powerful capabilities of decentralized applications, enabling real-time updates and user modifications through smart contracts. With everything set up, it's time to run our application. Make sure your local server is running, for instance, using Live Server in your code editor. Open the index.html file in your browser. You should see the current greeting displayed on the screen, along with an input field. Try changing the greeting message by entering a new greeting in the input box and clicking the Set Greeting button. Watch how the greeting updates dynamically without needing to refresh the page. This is the power of decentralized applications, offering real-time interactions powered by the blockchain. In conclusion, by building the greeter contract, we learned how to establish the foundation for creating smart contracts using Solidity. We implemented a simple greeting mechanism, deployed our contract to a local blockchain with Truffle, and interacted with it via a web-based interface. This experience emphasizes the power of blockchain technology and smart contracts in creating engaging user experiences. In our next session, we will explore more advanced topics, including error handling in smart contracts and deploying our DApp to a live network such as the Ethereum mainnet or a testnet. Thank you for joining me today, and let's keep the momentum going as we continue our journey into the Ethereum ecosystem. Now let's take a look at how we can implement ownership functionality in our Greta smart contract. We begin by introducing a new state variable called owner, which will hold the address of the contract's owner. This is crucial because only the owner should be able to make significant changes to the contract, such as updating the greeting message. In the constructor, we assign MSG sender to owner. This assignment captures the address of the account that deploys the contract, establishing a clear ownership link right from the beginning. By using MSG sender, we ensure that this account has full control over the contract, enhancing our security measures. The next step involves restricting access to specific functions so that only the owner can invoke them. To achieve this, we will create a modifier called onlyOwner. This modifier checks whether the caller, MSG sender, is the current owner. If not, the function execution will be halted, preventing unauthorized access. Finally, we will integrate this modifier into our setGreeting function, which allows the owner to update the greeting. This setup effectively secures our contract, ensuring that only the owner can modify the greeting message. Now let's see how we can implement the ownership functionality in our Greta smart contract using a modifier. To restrict access to the setGreeting function, we create a modifier called onlyOwner. This modifier checks if the caller of the function, MSG sender, is equal to the owner of the contract. If the caller is not the owner, the transaction will revert with the error message, "You are not the owner." The underscore placeholder at the end signifies where the actual function logic will execute if the requirement is satisfied. Next, we will incorporate this modifier into the setGreeting function. By adding onlyOwner to the function declaration, we ensure that only the designated owner can call this function to update the greeting message. If any non-owner attempts to execute this function, the transaction will fail, thus protecting the contract from unauthorized changes. This pattern enhances the security of our smart contract and fortifies the trustworthiness of the greeting message management, ensuring that only the appointed owner has the capability to modify it. Now let's see how we can implement a function to allow users to view the current owner of the Greta contract. We will create a public function called getOwner that returns the address of the contract's owner. This approach fosters transparency in decentralized applications, as users can easily verify who is managing the contract. By calling getOwner, anyone interacting with our contract can obtain the owner's address, enhancing trust in the system. Next, we need to ensure that the changes we've made to the contract, including ownership functionalities, are correctly deployed. To do this, we will utilize our migration script, and it's crucial to replace the existing Greta contract code in the GretaSol file with the updated version that contains the new ownership features. After updating the file, we will run the migration command with the reset flag. This flag ensures that all previous migrations are executed again, deploying the latest state of our contract and making sure our newly implemented ownership structure is established and tested effectively. Now let's take a look at how we can interact with our newly implemented Greta contract in the Truffle console. First, we need to retrieve the deployed instance of the Greta contract. By calling Greta deployed, we obtain the contract instance, which allows us to interact with its methods. We store this instance in a variable, Greta instance, for use in subsequent calls. Next, we want to check the current owner of the contract. This information is essential for ensuring that only the contract owner can make changes like updating the greeting. We invoke the getOwner function on our Greta instance, which returns the owner's address, and we log it to the console for verification. Now let's implement a feature to change the greeting message. By using the setGreeting method and passing a new greeting, we ensure that only the owner can execute this change, as enforced by the ownership control we implemented. Once the transaction is processed, we call the greeting function to fetch and display the updated greeting, confirming that the action was successful. This process provides a clear demonstration of the ownership model in action, highlighting the security of our contract. Now let's take a look at how we can test the ownership restriction of our Greta contract by simulating an interaction from a non-owner account. First, we define a variable called OtherCount, where you will need to replace the placeholder with the actual address of another account from Ganache. To enable this account to interact with the contract, we unlock it using the Web3 ETH personal unlock account method, providing the account password as well as specifying the duration for the unlock. Next, we attempt to change the greeting message by calling the setGreeting function from OtherCount. This invocation is done using the send from OtherCount method. Since OtherCount does not have ownership privileges, the transaction is expected to fail. We chain a then method to log a message indicating success, although we anticipate that it should not happen. To handle the failure, we provide a catch block that captures the error and logs the expected error message. This exercise effectively demonstrates how the ownable pattern protects our contract by preventing unauthorized access, ensuring that only the designated owner can update the greeting message. Now let's implement the transfer ownership function, which enhances the flexibility of our ownership model. This function allows the current owner to transfer their ownership rights to a new address. It begins by checking that the new owner's address is not a zero address, as this would be invalid in the Ethereum network. This is crucial because transferring ownership to a zero address could lead to a loss of control over the contract. We utilize the onlyOwner modifier to ensure that only the current owner can call this function, reinforcing the principle of restricted access that we established earlier. This step is vital to maintain security and prevent unauthorized transfers. If the address check passes, the owner state variable is updated to the new owner's address, effectively relinquishing control from the previous owner to the new one. Through this implementation, we ensure that ownership can be securely transferred while limiting this capability to the designated owner. This not only provides flexibility in contract management, but also strengthens the overall integrity of our Greta smart contract by maintaining control over who can make significant changes. Now let's implement the transfer of ownership functionality in our Greta contract. This feature allows the current owner to delegate ownership to a new address, enhancing the contract's usability in various scenarios. We will begin by defining a function called transfer ownership, which accepts an address parameter representing the new owner's address. To ensure that only the designated owner can invoke this function, we will utilize the onlyOwner modifier we created earlier, which verifies that the caller is indeed the current owner of the contract. Within the function, we also include a safeguard to check that the new owner's address is not a zero address, a common practice in Ethereum to avoid invalid states. By implementing this code, we empower the current owner to transfer control easily while maintaining security. This capability is crucial for decentralized applications, where administrative responsibilities may need to shift over time. Once this function is in place, we can seamlessly manage roles within our contract, ensuring that ownership can evolve in a controlled and secure manner. In conclusion, by implementing ownership in our Greta smart contract, we learned how to secure functions so that only approved addresses can execute certain actions. We discussed how to create a simple ownership model, added functionality to ensure only the owner can change greetings, and provided the ability to transfer ownership. These principles enhance the accessibility and security of our decentralized applications. In our next session, we will continue to build on these concepts, diving into advanced topics like error handling and deploying our DApp to live networks. With ownership secured, we are making essential strides toward effective DApp development, so stay tuned for more exciting content as we journey deeper into the world of Ethereum. Now let's see how we can implement the dynamic capabilities in our Greta smart contract. We will start by introducing a mapping that associates each user's address with their personalized greeting. This allows us to store multiple greetings, enabling individualized interactions. Instead of a single greeting variable, we'll use a mapping called greetings, which will hold the greeting for each address. Next, we'll write a function called setGreeting. This function allows users to save their chosen greeting by passing it as an argument. By utilizing MSG sender, we ensure that each greeting relates directly to the user invoking the function. Additionally, we will create a revised greet function that fetches and returns the greeting corresponding to the caller's address. This means that every user will receive their unique greeting whenever they call the greet function, enhancing the interactivity of our smart contract. Moreover, to ensure robustness, we will add validation to the setGreeting function to prevent users from setting an empty greeting. This ensures that only meaningful greetings can be stored, thus improving the overall user experience and reliability of our contract. Now let's implement the following updates in our Greta smart contract to allow users to set their personalized greetings. We begin by introducing a mapping called greetings, which maps a user's address to their specific greeting message, thereby allowing multiple users to interact with the contract without overwriting each other's greetings. Next, we will create a function named setGreeting that enables users to store their chosen greeting. This function takes a string input representing the greeting, and it uses MSG sender to identify the user's address. When a user calls this function, their input is saved in the mapping we defined earlier, establishing a unique greeting for each address. Now let's take a look at the greet function. This function retrieves the greeting associated with the address that called it. When a user invokes greet, they receive their personalized greeting, enhancing the interactivity and user experience of our smart contract. Overall, this dynamic implementation ensures that each user can store and retrieve their individual greetings, fostering a more engaging interaction with the smart contract. Next, we'll focus on redeploying our greeter contract to incorporate the new dynamic functionality we've added. To do this, we use the command truffle migrate reset, which ensures that our contract is redeployed, reflecting the latest changes. Once the deployment is successful, we can interact with our contract through the Truffle console. Now let's enter the console with Truffle console and retrieve the deployed greeter contract instance. This is accomplished by executing a promise that assigns the instance to a variable called greeterInstance. This step is crucial because it allows us to interact with the deployed contract directly. Now let's see how we can set a personalized greeting by invoking the setGreeting function on our greeterInstance and passing in the desired message. After executing this function, we notify the user that the greeting has been set successfully. Next, we will retrieve the greeting we just set by calling the greet function on the greeterInstance. This function will return the customized greeting, demonstrating how our contract manages greetings on a per-user basis, enhancing user engagement with a unique interaction for each individual. Now let's implement the following series of interactions that demonstrate how a dynamic greeting functionality works with multiple users. First, we allow account 1 to set their greeting by calling the setGreeting function on the greeterInstance and passing in their desired message, hello, Ethereum. This line ensures that account 1's greeting is stored in the contract's mapping, tied to their unique address. Next, we will switch gears to account 2 and similarly set its greeting, this time using the message, greetings, blockchain. By calling the setGreeting function again, but from account 2, we ensure that each user can maintain their unique greeting without affecting others. Now let's see how both accounts retrieve their greetings by calling the greet function. When account 1 invokes this function, the contract fetches the greeting associated with account 1's address, returning hello, Ethereum. In parallel, when account 2 calls the same function, it retrieves greetings, blockchain. This showcases the dynamic capability of our contract, allowing personalized greetings for each user and confirming that our implementation handles greetings on a per-user basis effectively. Next, we will write the modified setGreeting function, which incorporates input validation to enhance our contract's reliability. In this implementation, we utilize the require statement to ensure that the greeting provided by the user is not an empty string. By checking the length of the greeting input, we can guarantee that the transaction will revert if the greeting is empty, and it will display the message, greeting cannot be empty. This validation step is crucial as it prevents users from inadvertently overwriting their custom greetings with a blank entry. After validating the input, we store the provided greeting in the greetings mapping, which associates each user's address with their personalized greeting. This combination of error handling and user-specific storage strengthens our contract by ensuring that only valid inputs are accepted while allowing each user to maintain their individual greetings. So as users call this function, they can confidently update their greeting without the risk of leaving it blank, thus enhancing the overall user experience and the functionality of our greeter contract. Now let's see how we can implement a front-end interface using React to interact with our greeter smart contract. We start by importing necessary libraries such as React, Web3, and the greeter contract's ABI. The main app component initializes local state variables to hold the user's account and greeting. Using the useEffect hook, we load Web3 and fetch the user's Ethereum account when the component mounts. Next, we set up an event handler, handle greeting change, which updates the local greeting state as the user types into the input field. Now, let's implement the submit greeting function that will handle submitting the user's greeting. This function prevents the default form submission behavior, creates a contract instance with the ABI and address, and calls the setGreeting method on the smart contract. We also retrieve the updated greeting from the contract and display it dynamically below the form. Finally, the return statement renders the interface, featuring a title, input field for setting the greeting, and a display for the user's current greeting. This setup enhances user engagement by providing a seamless interaction with the greeter smart contract. Now let's see how we can enhance our greeter smart contract by introducing events that provide feedback when users set their greetings. First, we define an event called greetingSet that takes the user's address and the new greeting as parameters. This event is crucial as it allows external listeners, such as user interfaces or other contracts, to react whenever greeting is updated. Next, we modify the existing setGreeting function by adding the emit statement to trigger the greeting set event. When a user sets a new greeting, this function ensures the input is valid by checking that it is not empty. If the greeting passes this check, it updates the greeting mapping for that user by utilizing MSG sender to identify the caller. Finally, the newly added event is emitted, broadcasting the user's address along with their updated greeting. This incorporation of events not only enhances the interactivity of the contract, but also provides valuable real-time information to anyone monitoring the contract, making it suitable for more complex applications where multiple greetings might be set by different users. To wrap it all up, by making our Greet Smart contract dynamic, we opened up avenues for user interaction and personalized experiences. We introduced functionality that allows users to set individual greetings, implemented input validation for better security, and discussed how to enhance the front-end interface for usability. In the subsequent lessons, we'll delve into even more advanced topics, including error handling mechanisms and deploying our decentralized applications to live networks. These enhancements will elevate our projects, ensuring they are not just functional, but also robust and user-friendly. Thank you for following along, and I hope you're excited to see how we can extend our smart contract capabilities even. Next, we will write the configuration needed for deploying our smart contracts to the Ganache blockchain. This configuration is crucial as it informs Truffle how to connect to the local Ethereum network you've set up with Ganache. The first part defines a module export, which is standard practice in JavaScript to allow other parts of your application to use this configuration. Within it, we specify networks, focusing on the development network, which is where our contracts will be deployed. Here, we set the host to 127001, which refers to our local machine, indicating that Ganache is running locally. Next, we specify the port number, 7545, which is the default port for the Ganache GUI interface. For users running Ganache CLI, this would typically be 8545, so it's essential to adjust based on your setup. Lastly, we set the network ID to, which means it will match any network ID, allowing us flexibility in case we make adjustments or deploy to different test networks later. With this configuration, Truffle is now ready to communicate with Ganache, enabling us to deploy and manage our smart contracts effectively in a safe and cost-free environment. Next, we will write the following commands to prepare our smart contracts for deployment. The first command, Truffle compile, compiles your contracts, turning the Solidity code into bytecode that Ethereum can understand, while also generating an ABI, which describes how to interact with the contract. This process ensures that all your changes are captured and ready before deployment, and the compiled artifacts will be stored in the build contracts directory for future use. After successfully compiling your contracts, we will run the subsequent command, Truffle migrate network development. This command initiates the deployment of your compiled contracts onto the specified network, in this case, Ganache. During this step, Truffle executes migration scripts located in the migrations directory, which handle the deployment of various contracts in the appropriate sequence. By executing this command, you should anticipate output that includes transaction hashes and gas usage details, confirming that your contracts, including the critical migrations and Greta contracts, have been successfully deployed to the local blockchain. After migration, you will be able to interact with your contracts directly through your front-end application. Now let's take a look at the output you can expect after deploying your contracts to Ganache. When you initiate the migration process using the Truffle migrate network development command, you'll see a summary of the deployment process. This output begins by confirming the network name as development and providing a unique network ID, in this case 5777, which identifies your local Ganache blockchain. Following that, you will see details about each migration script that Truffle runs. The first one initial migration. JS deploys the migrations contract, which is crucial for tracking which migrations have been executed. This section provides a transaction hash for the deployment, confirming that it has been processed on the blockchain alongside key metrics like the number of blocks mined, the duration of the transaction, and the gas used for deployment. For the second migration, you will observe the deployment of your Greta contract. The output includes similar details, allowing you to track the transaction associated with this deployment. It's important to note the contract addresses displayed for both contracts, as you'll need to reference these addresses later to interact with your deployed contracts. This information will be vital for performing functions, sending transactions, and verifying that your contracts are functioning as intended. Now let's implement the following commands to restart our node server after successfully deploying our smart contracts to Ganache. Begin by navigating into your client directory using the command cd client. This step is crucial as it ensures that your terminal is pointed to the correct folder where your front-end application resides, which will interact with the deployed smart contract. Next, we will initiate the node server with npm run start. This command will compile and run your application, allowing the server to listen for incoming requests on the specified port, typically port 3000. After executing these commands, you will be able to view the Greeter UI in your web browser by visiting localhost 3000. The Greeter UI is the front-end interface that will display the default greeting of "Hello, World." This interaction serves as an immediate test of your smart contract's functionality by confirming that it can send and retrieve greeting messages. By using the input field provided, you can update the greeting message, demonstrating how the contract allows for dynamic interaction based on user input. This live feedback ensures that your smart contract's logic is processing correctly in a user-friendly environment. Do note that while Ganache is an excellent tool for testing, it is still a local environment. When you are ready to share your contract with others for testing or to move to a live environment, you will need to deploy on a public test network like Ropsten or Rinkeby. In closing out our exploration of deploying to Ganache, remember the importance of testing your smart contracts thoroughly before moving onto a public network. Ganache allows you to experiment, adjust, and troubleshoot your contracts without incurring costs, making it an invaluable tool for the developer toolkit. Now we are ready to move on to even more advanced topics, where we will cover how to handle errors and exceptions in Solidity, ensuring that our smart contracts are robust and production-ready. Exciting. Now let's take a look at the configuration code needed to connect Parity to the Goerli test network. The first part specifies the network settings. Setting the chain to Goerli directs Parity to establish a connection to the Goerli test network, enabling essential features like remote procedure call, RPC, and WebSocket support for interaction with smart contracts. The RPC setting allows your application to make HTTP requests, while WebSockets facilitate real-time communication, making it easier to fetch updates from the blockchain. Next, we define the RPC server under the RPC section, where the specified port of 8545 enables your local machine to listen for incoming requests. Additionally, the bind IP is set to 127.0.0.1, which restricts access to the local host for security. The cause setting, configured to allow all domains with the wildcard symbol, ensures that your front-end application can communicate seamlessly with the blockchain. This configuration snippet is vital for setting up a robust environment that facilitates interaction with the Goerli test network, making the deployment process smoother and more efficient. Now let's see how we can implement the migration script for deploying the Greeter contract on the Goerli network. First, we define the Greeter contract by requiring its artifacts, which are generated upon compilation. This step is critical as it ensures that we are working with the most current version of our contract. The next part of the script consists of a module export function, which Truffle uses to manage the deployment process. Here, we call the deploy method provided by Truffle's deployer object to initiate the contract deployment. In this case, we are not just deploying the contract, we are also initializing it with a default greeting message, "Hello, Goerli." This initialization is essential because it sets the initial state of the contract as soon as it is deployed. By passing this greeting to the constructor of the Greeter contract, we ensure that users interacting with the contract will receive a warm welcome as soon as they call the greeting method. This simple but effective script plays a vital role in managing how and when our contract is deployed to the network, aligning perfectly with our deployment strategy on Goerli. Now let's see how we can configure the Goerli network settings in our Truffle config.js to enable seamless deployment of our contracts. We begin by importing the HD wallet provider and Web3 libraries, which allow us to manage our wallet connections and interact with the Ethereum blockchain respectively. The Infura key and mnemonic variables must be defined, where you will replace YOUI and FURA key with your actual Infura project ID and your mnemonic with the mnemonic phrase from your wallet. This configuration creates an object specifying the Goerli network under the network's key. The provider function initializes the HD wallet provider using the previously defined mnemonic and sets up the Infura endpoint for network access. Importantly, we specify the network ID for Goerli as 5, set a gas limit of 5,500,000, and define parameters to wait for 2 confirmations between deployments. The option to skip the dry run is also included, which can expedite the migration process during live deployments. Next, we will write the command for deploying the contract to the Goerli network, which can be run directly in the terminal. This step is crucial, as it initiates the actual deployment process while ensuring all configurations are correctly utilized for a successful interaction with the Goerli test network. Now let's see how we can implement interaction with the Greta smart contract using JavaScript and the Web3.js library. First, you'll need to install Web3.js, which is the Ethereum JavaScript API that enables communication with your deployed smart contracts. After installation, we import the Web3 library into our script. Next, we establish a connection to the Goerli test network via an Infura endpoint. This requires using your unique Infura project key to ensure secure access. Once this connection is set up, we define the Greta contract's address, which you should have obtained during the deployment phase. Additionally, you'll need the ABI application binary interface for the contract, which describes the methods and structures of the smart contract. With both the contract's address and ABI at hand, we create an instance of the Greta contract. This instance allows us to interact with the smart contract's functions. In this case, we invoke the greet method, which will retrieve the greeting message from the contract. To handle the response, we utilize a promise that logs the greeting to the console if successful, or catches and logs any errors that arise, demonstrating how to manage interactions with your deployed smart contract effectively. Deploying to networks like Goerli simulates a real-world environment, providing vital testing grounds before a full mainnet deployment. However, do remember that deploying on test networks still incurs gas fees, albeit they are paid with test ether. It's essential to understand how to manage your contract states and handle potential errors that may arise in these environments. This leads us nicely into our next lessons, where we will discuss how to handle errors effectively within Solidity contracts. Proper error handling is crucial in smart contract development and can save you a great deal of headache when things don't go as planned. To create robust contracts, understanding design patterns that anticipate user error is key. So as we transition into our next topic of discussion, remember that successful smart contract development transcends merely writing code. It involves thorough testing, auditing, and preparation for the inevitable issues that may arise as your applications scale. Keep exploring, and let's ensure our contracts are the best. Now let's take a look at how to configure our Truffle project for deployment on the Rinkeby test network using Infura. We begin by installing Truffle globally, which is essential for managing our smart contract development and deployment process. Following the installation, we will navigate to the Truffle config.js file located in the root directory of our Truffle project. This file acts as the command center, where we define network configurations. Next, we will add the Rinkeby network configuration to this file. This includes setting up the HD wallet provider, which acts as a bridge between your wallet and the Rinkeby network. We will need to replace the placeholders with our actual Infura project ID and the mnemonic from our wallet, ensuring to keep this information confidential. The configuration specifies vital parameters, such as the network ID for Rinkeby, gas limits, and whether to skip the dry run before migrations. This setup allows Truffle to deploy our smart contracts seamlessly to the Rinkeby network, simplifying the entire deployment process. Now that we have our Greta smart contract ready, let's look at how this contract works and what features it includes. The contract begins with a declaration of its license and the Solidity version, followed by the definition of the Greta contract itself. We have declared a state variable called greeting, which is of type string and will hold the greeting message. Next, we implement the constructor, which is a special function that initializes the contract when it is deployed. It takes a string parameter, greeting, and assigns it to the greeting variable. This allows us to set an initial greeting message when deploying the contract. We then define two functions, greet and setGreeting. The greet function is a public view function that allows us to read the current greeting message stored in the contract. When called, it returns the value of the greeting variable. On the other hand, the setGreeting function allows us to update the greeting message. This function can be called by any user, enabling them to change the greeting stored in the contract. Now that we understand the structure and functionality of our Greta contract, let's compile it using Truffle to prepare it for deployment on the Rinkeby network. Now that we've set up our Infura configuration and are ready to deploy the Greta contract, we'll need to create a migration script. Next, we will write a JavaScript file named toDeployGreta.js in the migrations folder. This script is crucial for automating the deployment of our smart contract to the Rinkeby network. In this script, we first require the Greta contract using Truffle's Artifacts API. This step allows us to access the compiled version of the contract, which contains all the necessary information for deployment. After that, we use a module export to define a function that accepts a deployer parameter. This deployer is a part of the Truffle framework responsible for managing the deployment process. Here we call the deployer deploy function, passing in the greeter contract and initializing it with a greeting message, hello Rinkeby. This step ensures that when the contract is deployed, it will store this initial greeting on the blockchain. Now we need to deploy our contract to Rinkeby. To do this, we will use the migration command with the Rinkeby network flag in our terminal. As the command executes, the terminal will display logs outlining the deployment status and the transaction hashes, which are essential for tracking the deployment on the network. Now let's take a look at how we can interact with our deployed greeter contract using Web3.js. First, we need to ensure that we have the Web3 library installed to enable our JavaScript application to communicate with the Ethereum network. Next, we establish a connection to the Rinkeby test network by creating a new instance of the Web3 object and pointing it to our Infura endpoint, which allows us to send requests without running our own Ethereum node. It's crucial to replace your infura projected with your actual Infura project ID for the connection to work. After setting up the connection, we define two important pieces of information: the address of our deployed contract and the ABI application binary interface. The contract address is where our greeter contract resides on the blockchain, while the ABI is essential as it outlines the contract's interface, detailing the methods that can be called. Now let's implement the function to fetch and display the greeting from the contract. We call the greet method asynchronously, which interacts with the deployed greeter contract to retrieve the current greeting. Upon receiving the response, we log it to the console, allowing us to see the result of our interaction with the blockchain. This straightforward setup showcases the power of Web3.js in bringing our decentralized applications to life. Now let's implement the code necessary to interact with our deployed greeter contract using Web3.js. In this script, we begin by importing the Web3 library, which allows us to interact with the Ethereum network. Next, we establish a connection to the Rinkeby test network via the Infura endpoint, using the project ID you've obtained from your Infura account. This connection is crucial as it facilitates communication between your application and the Ethereum blockchain without the need for a local node. Following the connection setup, we specify the address of our deployed greeter contract and include its application binary interface, ABI. The ABI is essential as it provides a structured format that defines the contract's functions and their parameters, enabling our script to understand how to interact with the contract. Now let's look at how to define a function named greet, which we'll call the greet method of our greeter contract. When executed, this async function fetches the current greeting stored within the contract and logs it to the console. This step connects our application to the blockchain, allowing us to retrieve state data from our smart contract seamlessly. Once everything is set up correctly, we'll run the script using Node.js to see our greeting. Our application is designed to assist beneficiaries such as nonprofits and various entities seeking funding. The aim is to create a decentralized fundraising platform that not only allows for transparent transactions, but also ensures that all parties involved can participate smoothly and securely. So far, we have covered deploying smart contracts to the Goerli and Rinkeby test networks using different methods, managing our configurations, funding test accounts, and successfully interacting with the deployed contracts through Web3.js. Now, we will dive deeper into creating a fundraiser application where beneficiaries can receive donations via Ethereum, track balances, and even manage custodian interactions. We will explore Solidity features such as constructors, events, and state management while building our application. Now let's take a look at the implementation of our Fundraiser smart contract, which serves as the backbone for managing fundraising initiatives on the Ethereum blockchain. We start by defining important state variables that hold essential information about the fundraiser, including the name, URL, image URL, description, and the beneficiary's address. The beneficiary's address is marked as payable so that it can receive donations in Ether. Next, we introduce a constructor function that initializes these variables when a new instance of the fundraiser contract is created. This means whenever someone sets up a new fundraiser, they'll need to provide this crucial information, ensuring that everyone has the necessary details readily available. As we advance, it's critical to enable external access to these state variables. By declaring them as public, Solidity automatically generates getter functions, facilitating easy retrieval of these details from our user interface. This approach is key to creating a user-friendly and informative experience for potential donors, providing transparency and accessibility right from the start. Now let's take a look at how we can implement the function to create a new fundraiser. This JavaScript function, named createFundraiser, is designed to gather information from specific input fields in our user interface. It efficiently collects data such as the fundraiser's name, URL, image, description, beneficiary's address, and custodian's address from their respective HTML elements using document getElementById. After collecting this data, the function calls the smart contracts create fundraiser method, passing in the gathered information as arguments. This method is crucial as it facilitates the interaction between the front-end application and the deployed smart contract on the blockchain. The send method is subsequently invoked to initiate the transaction, specifying the sender's Ethereum account, typically the user's account from which the transaction will be submitted. Implementing this function bridges the gap between users and the decentralized platform, allowing them to submit their fundraising proposals easily. This enhances user engagement by enabling them to interact directly with the blockchain, reinforcing the transparent and secure nature of our fundraising solution. Now let's see how we can implement the donation tracking system for our fundraiser application using Solidity. We start by defining a donation struct, which will securely store essential information about each donation, including the amount donated and the exact timestamp when the donation was made. This structure allows us to maintain a clear record of donations tied to each user. Next, we utilize a mapping to link each user's address to an array of donation records. By doing this, we create a comprehensive donation history for every individual contributor, enabling us to easily retrieve their past donations. This design choice not only enhances transparency, but also allows for a straightforward way to track fundraising efforts over time. Moving forward, we will write a function to facilitate donations from users. This function is designed to check that the donation amount is greater than 0, ensuring valid input. Once the donation is accepted, it updates the user's donation history, allowing us to see who contributed what and when. Additionally, we will emit an event to log each donation, providing valuable data for external applications that may want to track donation activity. Now that we have our donation tracking structure in place, let's implement a function that enables users to make donations. We will create a donate function, which allows users to send Ether to the contract while ensuring input validation. Within this function, we start by checking that the donation amount is greater than 0, using a require statement. This step is crucial to prevent any errors that may arise from invalid or unexpected input. Upon successful validation, a new record is created to document the donation, capturing both the amount sent and the timestamp of the transaction. This record is appended to an array that maintains the donation history for the sender, allowing us to keep track of individual contributions over time. Additionally, we will emit a donation received event to log important details about the transaction, making it accessible for any off-chain applications that may need to track donations. Emitting this event not only helps in ensuring transparency, but also provides confirmation to the donor about their contribution. Overall, this functionality lays the groundwork for transparent and secure donation handling within our fundraising platform. Now let's examine how we can implement event logging for our fundraising application. We will define an event called donation received, which takes two parameters, the address of the donor and the amount donated. By including the keyword indexed with the donor parameter, it allows for efficient filtering of log entries based on the donor's address later on. This is crucial as it enables off-chain applications and user interfaces to listen for and respond to donation events in real time. When a donation occurs through our donate function, we will emit this donation received event to signal that a new donation has been made. This acts as a confirmation for the donor, who will want to see a record of their transaction, enhancing the user experience. The emitted events serve as a decentralized receipt, ensuring transparency as they can be tracked on the blockchain. Overall, using events not only reduces on-chain data storage costs, but also promotes a responsive interface for our donors, allowing them to feel confident and informed about their contributions to the fundraiser. Now let's implement the withdrawal functionality, which is crucial for ensuring the secure handling of funds accumulated through donations. The withdraw function is a key component of our fundraiser contract, designed exclusively for the contract owner or custodian. This function begins by checking if there are any funds available for withdrawal using a require statement. If the contract's balance is greater than 0, it proceeds to transfer the entire balance to the beneficiary's address. This critical check not only prevents errors, but also reinforces the security of the funds, ensuring they cannot be accidentally accessed without authorization. The use of the onlyOwner modifier is significant here, as it restricts the ability to call this function solely to the owner of the contract, further protecting the funds. By allowing only authorized parties to withdraw money, we add a layer of trust and security to the transaction process. This aligns with the overarching goal of our application, to foster a transparent and user-friendly fundraising environment while safeguarding the integrity of the donations. It's vital to test our application thoroughly. Utilizing frameworks like Truffle, we can run unit tests to ensure each aspect of our contract, the initialization, the donation logging, the event emissions, and the withdrawal, is functioning correctly. Good tests will confirm that our constraints are enforced, such as only allowing the owner to withdraw funds and ensuring non-zero donations. In summary, we've built a robust foundation for a blockchain-based fundraising application that facilitates secure donation tracking and transfers. Next up, feel free to jump into advanced concepts, including integrating front-end technologies for a seamless user experience. In today's lesson, we'll focus on an important functionality of our decentralized fundraising platform, transferring the balance of the smart contract to the beneficiary. This feature ensures that once the funds are raised, the rightful owner can access them securely and efficiently. So far, we learned about building a decentralized fundraising platform that facilitates donations through Ethereum while ensuring transparency and security. We explored deploying smart contracts and their structures, including essential properties for fundraiser contracts. We focused on managing donations, tracking donation history, and implementing key functionalities like donation processing and fund withdrawal. Our next steps will delve into advanced concepts and integration with front-end technologies for enhanced user experience. Understanding how to manage funds properly in a smart contract is crucial for any blockchain application. Once a fundraiser collects donations, the next logical step is to ensure those funds can be transferred to the beneficiary. This function is not merely a convenience, it's key to the operational integrity of your smart contract. In Solidity, we implement this functionality by creating a withdrawal function. Before diving into the coding part, let's discuss what we need to consider for this function. First and foremost, it's essential to verify who has the authority to withdraw the funds. This is typically the beneficiary or a designated custodian. This is a security measure to ensure that only authorized addresses can access the collected funds, minimizing the risk of unauthorized withdrawals. The next component of our withdrawal function is to check that there are indeed funds available for withdrawal. This can be done by querying the Ether balance of the contract itself. Now let's dive into the implementation of the withdrawal function in Solidity, a crucial component of our fundraising smart contract. This function begins with a visibility modifier, specifically public, which allows it to be called both internally and externally. The only owner modifier ensures that only the contract's owner can access it, adding a layer of security to protect the funds. Next, the function includes a require statement that checks whether the contract's balance is greater than 0. This validation is critical because it prevents the withdrawal from occurring if there are no funds available, thus avoiding any unexpected behavior during execution. If this condition is not met, the transaction will revert with the message, "No funds to withdraw," providing clear feedback to the caller. Finally, if all checks are passed, the function executes the line that transfers the entire Ether balance of the contract to the designated beneficiary. This effectively sends the raised funds to the rightful owner, completing the withdrawal process securely. By following these steps, we ensure that only authorized withdrawals take place, maintaining the integrity of our fundraising platform. Next, we will implement event logging for our withdrawal function, which is crucial for maintaining transparency in our blockchain application. First, we define an event called withdrawal that captures the address of the beneficiary and the amount withdrawn. The address indexed to parameter allows us to filter the event by beneficiary addresses easily, making it more efficient to track specific withdrawals later on. Now let's take a look at how we can log an event every time the withdraw function is executed. By using the emit keyword followed by withdrawal beneficiary address this balance, we fire the event with the current contract balance being sent to the beneficiary. This line ensures that whenever the withdrawal occurs, an event is emitted to the blockchain, providing an immutable record of withdrawals. Incorporating these events into our contract not only aids in accountability, but also enables external applications to react to these events, enhancing user experience and trust in our platform. Overall, proper event logging is a vital component of smart contract development to ensure that all actions taken within the contract are transparent and traceable. Now let's implement a modifier to enhance the security of our withdrawal process. The only beneficiary modifier serves as a critical gatekeeper, ensuring that only the rightful beneficiary can trigger the withdrawal of funds from the smart contract. Inside this modifier, we use a requirement statement to check if the sender of the function call is indeed the designated beneficiary. If the check fails, the function call is reverted with an appropriate error message, preventing unauthorized access to the funds. Following this definition, we can add the only beneficiary modifier to our withdraw function, effectively enforcing this security measure. By integrating this modifier, we enhance the trustworthiness of our smart contract, ensuring that only authorized individuals can execute potentially sensitive actions like fund withdrawals. The notation acts as a placeholder, allowing us to incorporate this additional layer of validation before proceeding with the execution of the withdrawal logic. This approach not only secures the withdrawal process, but also fosters confidence among users regarding the integrity of their funds in the contract. Now let's see how we can implement the withdrawal request feature for our fundraising platform. In the provided code, we define an asynchronous function named requestWithdrawal. The use of the async keyword allows us to handle operations that involve waiting for external processes, such as blockchain transactions. Within this function, we call myContractMethodsWithdraw, which directly references the withdraw method we've implemented in our smart contract. This action triggers the entire withdrawal process, transferring the funds to the authorized beneficiary. The send from account 0 part of the code specifies the originating address for this transaction, ensuring that the request is executed from the correct account. It's crucial to incorporate error handling to enhance user experience. By properly managing the potential exceptions that may arise during the transaction, we can ensure that users receive feedback whether their withdrawal attempt is successful or if an error has occurred. This enhances transparency and builds trust, ultimately improving the overall interaction users have with the platform. Now, let's implement a user-friendly notification system to inform users about the status of their withdrawal transactions. The provided code snippet uses a try-catch block to handle the withdrawal request effectively. In the try block, we attempt to call the withdraw function from our smart contract using the myContractMethodsWithdraw_send method. This action triggers the withdrawal process that we previously established in the smart contract, where the beneficiary can withdraw the funds. If the transaction is successful, the alert function notifies users with a message indicating that their withdrawal was successful, enhancing the overall user experience. However, if an error occurs during the transaction, perhaps due to insufficient funds or access restrictions, the catch block captures the error. Here, we construct a user-friendly alert that provides feedback detailing the specific error encountered. This two-pronged approach not only confirms successful transactions, but also reassures users by transparently communicating any issues, thus helping to maintain trust in our platform. Overall, this method significantly contributes to ensuring a responsive and engaging user interface for our fundraising platform. Now let's see how we can implement testing for our smart contracts withdrawal functionality. We begin by requiring the fundraiser contract to access its functionalities for testing. Inside our test suite, we set up the contract instance before each test. The before each function ensures we deploy a fresh instance of the fundraiser contract, along with initializing conditions like simulating a donation from an account. This setup is crucial as it provides a controlled environment to validate our contract's behavior. Next, we focus on testing the actual withdrawal functionality. We define a test case that specifically checks whether the beneficiary can withdraw funds as expected. When executing the withdrawal function, we expect the beneficiary's request to succeed, and to verify the correctness of our logic, we assert that the balance of the fundraiser contract becomes 0 afterward. This confirms that the funds have been successfully transferred to the beneficiary. Overall, this structured approach to testing ensures that our withdrawal feature operates as intended, reinforcing the integrity of our smart contract's core functionalities. As we wrap up this lesson, remember that facilitating a secure withdrawal process is not just a back-end concern. It's about creating a trustworthy experience for users engaging with your fundraising platform. Utilizing modifiers to protect sensitive functions, logging events for accountability, and integrating a seamless front-end experience contribute to an overall robust system. In future discussions, we will delve deeper into user experience enhancements and explore the intricate features of front-end frameworks that will make our platform not only functional, but also intuitively user-friendly. It's been a pleasure guiding you through the intricacies of smart contract functionality today, and I look forward to our next lesson, where we'll craft dynamic user experiences together. In this video tutorial, we will dive into the exciting world of event handling in our decentralized fundraising platform. Buckle up as we explore how events help us track important actions, such as when donations are made, ensuring a robust and transparent experience. So far, we learned about implementing a secure withdrawal function in our decentralized fundraising platform, ensuring only authorized beneficiaries can access funds. We discussed the importance of event logging for accountability and transparency, and explored how to integrate user interface elements with Web3, JS to facilitate user interactions. Additionally, we touched on the significance of testing our smart contract to validate functionality. Our next steps will include enhancing the user experience with advanced front-end features. Now let's implement the donation received event in our smart contract. This event is crucial as it logs significant actions related to donations, allowing external applications to track these occurrences effectively. By defining the event with the address index donor and UINT 256 amount, we capture the donor's address and the donation amount, respectively. The indexed keyword is particularly important as it enables us to filter the events based on the donor's address later, facilitating easier access to specific donation records without sifting through all emitted events. Once we've defined this event, we will trigger it after processing a donation in the contract. This ensures that every time a donor contributes, the transaction not only updates the total funds raised, but also emits the donation received event, providing an immediate log entry on the blockchain. This way, we'll maintain transparency and accountability for contributions made, enhancing the overall user experience in our fundraising platform. The ability to listen for this event from the front end and display real-time donations to users adds an interactive layer, fostering engagement and trust within the community. Now let's see how we can implement the donation processing function in our smart contract. In this function, we start by making sure that any donation received is greater than 0, which is enforced using the require statement. This statement is crucial because it ensures that invalid transactions are aborted immediately, maintaining the integrity of the contract. Next, if the donation is valid, we proceed to update our total funds raised variable by adding the incoming donation amount, represented by MSG value. This effectively tracks the cumulative funds raised by the platform. Once we've recorded the donation, we utilize the emit keyword to trigger our donation received event. This is a vital step, as emitting an event allows external applications and interfaces to listen for this significant action, like a donation being made. We pass MSG sender as the donor's address and MSG value as the donation amount so that accurate details are logged on the blockchain. With this setup, we ensure both accountability and transparency in our fundraising efforts, creating an engaging experience for users who want to track their contributions in real time. Now let's see how we can implement an event listener for our donation received event in Web3 JS. This line of code calls the events method on our smart contract instance, specifically targeting the donation received event. To ensure we only retrieve relevant events, we add a filter for a specific donor's address, which allows us to track donations made by that particular user. By setting the from block property to 0, we indicate that we want to start listening from the Genesis block, meaning we won't miss any donations. The second part of this code is a callback function that handles incoming events. Inside this function, we handle potential errors by logging them to the console, ensuring that if something goes wrong while fetching events, we are immediately aware of it. Conversely, if the event is successfully captured, we log the donation details to the console using the event return values, which contains the information emitted by our smart contract. With this setup, we create a transparent environment where users can actively see their contributions as they occur, enhancing engagement and fostering trust in the platform. Now let's implement the following code to enhance user feedback after a donation is made. We set up an event listener for the donation received event emitted from our smart contract. When this event is captured, our JavaScript function will react accordingly, enabling us to provide immediate notifications to the donor. Inside the onData callback, we access the details of the donation using event return values, which gives us the donor's address and the amount donated. We then dynamically update an HTML element, specifically the one with the ID donation status, to display a personalized message of gratitude. This message not only thanks the donor for their contribution, but also specifies the donation amount in Ether. By incorporating this feature, we create a real-time feedback loop that enhances the user experience, making donations feel more engaging and appreciated. Additionally, the on-error, console error line ensures that any potential errors during event listening are logged to the console for debugging, contributing to a robust implementation. Now let's see how we can gather the donation history for a specific donor using the getPastEvents method. This function allows us to query all the events related to donations that occurred within our smart contract, applying specific filters to hone in on the data we need. In the code, we are fetching all donation received events, filtering them by the donor's address to ensure that we only retrieve relevant donations. By specifying from block 0, we indicate that we want to start our search from the very beginning of the blockchain, and to block, latest tells the function to include events up until the most recent block. In the callback function, we handle errors by logging any issues to the console, ensuring that we can troubleshoot any problems that may arise during data retrieval. On success, the function will output an array of past donations linked to that specific address, allowing us to track the donor's contributions effectively. This capability enhances transparency within the fundraising process, enabling users to review their donation records effortlessly and fostering accountability. Implementing event handling not only creates interactivity for users, but also ensures that our smart contract adheres to the principles of transparency. By logging donations and providing a mechanism to view them, we're fostering trust within our decentralized fundraising community. This is essential as users will have more confidence knowing they can track their contributions and see the impacts in real time. In addition, effective use of events can contribute to the overall performance of our platform. Leveraging event loggers minimizes the need for constant state checks or polling, significantly improving the user experience while optimizing network utilization. As we wrap up this session, remember that events are a critical component of Ethereum smart contracts, providing visibility and interactivity to your decentralized applications. Today, we covered how to define and emit events, lesson for them using Web3, JS, and display real-time notifications for donations. We also saw how to pull past events for comprehensive donation history tracking. These skills are fundamental in creating a dynamic and engaging user experience in a decentralized fundraising platform. Moving forward, we can explore ways to enhance our UI further, such as incorporating charts or graphs to visualize fundraising progress. Thank you for joining me today, and I look forward to our next session where we will take our platform to the next level. Let's dive into the creation of the fundraiser contract, where a digital fund management transformation happens. We've already discussed how a decentralized fundraising platform facilitates donations while ensuring transparency through event handling. Today, we'll explore the inner workings of the fundraiser contract itself, where the actual magic of fund collection and distribution occurs. So far, we covered the importance of event handling, focusing on how donations are tracked and reported. In this lesson, we will cover the creation of the fundraiser contract, detailing its functionalities related to donations and fund withdrawals, and how we can create a robust, efficient, smart contract for our needs. Next, we will write the fundraiser contract code, where the essential elements for handling donations and fund withdrawals come together. The contract begins by declaring the necessary variables, including a payable address for the beneficiary, who will receive the funds, a total donations variable to track the cumulative amount raised, and a mapping named donations that records the amount contributed by each individual donor. The constructor initializes the contract, setting the beneficiary's address during deployment, ensuring that it is appropriately designated for future fund transfers. Now let's implement the donate function, which allows anyone to contribute to the fundraiser. This function checks that the amount donated is greater than 0 to prevent invalid transactions. Upon successful donation, it updates the individual donation record and increments the total donations, while also emitting an event to log the donation details for transparency. Next, we will look at the withdraw function, which enables the beneficiary to withdraw the total funds collected. This function enforces a restriction to ensure only the designated beneficiary can execute it. After confirming the address, it calculates the contract's balance and transfers the total amount to the beneficiary, while also emitting an event to record the withdrawal, reinforcing accountability within the contract's operational flow. Next, we will delve into the donate function, which plays a pivotal role in our fundraiser contract by processing incoming donations. In this function, we verify that the contribution being made is greater than 0 using the require statement. This check is essential as it prevents users from making invalid, zero-value transactions that could compromise the integrity of our donation tracking system. If the requirement is met, we proceed to record the donation by updating the donations mapping, which tallies the amount each user has contributed. Additionally, we increment the total donations variable to maintain an accurate running total of all funds collected. To enhance transparency and provide real-time updates, we utilize an event called Donation Received. When a donation occurs, this event emits the donor's address and the amount contributed, allowing anyone to verify donations via Block Explorer. This systematic approach to donation handling not only secures our contract's functionality, but also fosters trust among users by keeping thorough documentation of all transactions made. Thus, the donate function embodies the core mechanics of our fundraising mechanism, while ensuring accountability and user confidence. Now let's move on to the withdrawal functionality through the withdraw function. This function is crucial as it ensures that only the designated beneficiary can access the funds collected through the contract, which we enforce with a require statement that checks the sender's address against the beneficiaries. Next, we calculate the contract's balance using address this balance, allowing the beneficiary to determine the available funds for withdrawal. Once the beneficiary invokes this function successfully, the total balance is transferred directly to them via the beneficiary transfer amount line. This seamless transfer of funds is a core feature of the contract that reinforces its usability. After the transfer is executed, we emit a withdraw event, which logs both the beneficiary's address and the amount withdrawn. This event serves as a transparent record that can be verified on the blockchain, ensuring that both donors and the beneficiary can track transactions. Overall, this withdrawal mechanism highlights the contract's focus on security, usability, and transparency, key elements of our decentralized fundraising platform. Now let's implement the factory pattern to create our fundraiser contracts dynamically. In the Fundraiserfactory contract, we start by defining an array that stores the fundraiser contracts deployed, making it easy to manage multiple instances. We also declare an event, fundraiser created, which will notify when a new fundraiser is instantiated. Next, we'll create the function createFundraiser. This function allows anyone to deploy a new fundraiser contract by calling it. Inside this function, we instantiate a new fundraiser contract, passing in the caller's address as the beneficiary, which is essential as it establishes who will receive the donations. Once the new fundraiser is created, we push its address into our fundraisers array, ensuring we maintain a record of all deployed fundraisers. Finally, we emit the fundraiser created event, providing transparency by notifying listeners with the address of the newly created fundraiser. This factory structure not only simplifies the process of launching fundraisers, but also streamlines record keeping and event notification, highlighting the advantages of smart contracts within decentralized finance. Now let's implement the testing suite for our Fundraiserfactory contract using the Truffle framework. The contract function defines a test for the factory, specifying Fundraiserfactory as the contract to test and accounts as the predefined Ethereum accounts available during testing. Inside this structure, we'll create a variable to hold our factory instance, ensuring it's accessible across the different tests. Next, we use the before hook to deploy the Fundraiserfactory contract before running our tests, preparing our testing environment. This setup guarantees that the factory is correctly instantiated each time the tests run. Now let's see how we can verify if our fundraising functionality works as intended. In our first test case, we invoke the createFundraiser function from the factory instance. This creates a new fundraiser contract, which should result in an increase in the length of the fundraisers array. We assert that this length equals 1, confirming that a fundraiser contract has indeed been created. Additionally, we can extend our testing suite to include scenarios for donations and withdrawals, verifying that only the authorized beneficiary can withdraw funds and that donations are properly recorded. This comprehensive approach strengthens our contract's reliability, ensuring each function operates according to its defined logic. Now let's see how we can implement the test for the fundraiser contract's withdrawal functionality. In this test, we first create a new fundraiser instance through the factory, ensuring that the process of fund management can be initiated. We then retrieve the address of the newly created fundraiser and prepare to make a donation to it. This simulates a real-world scenario where a user supports the fundraiser by donating Ether. Next, we focus on the critical aspect of ensuring that only the beneficiary can execute the withdrawal function. After the donation is successfully made, we attempt to invoke the withdrawal process, specifying the beneficiary's address as the sender. This setup tests if the smart contract enforces its rules correctly. Finally, we check the contract's balance to confirm that all the funds have been withdrawn by the beneficiary, affirming that the withdrawal functionality operates as intended. By asserting that the balance equals 0, we validate that the test effectively confirms the intended behavior of the contract, thus solidifying the reliability of the fundraiser contract within our decentralized framework. As we wrap up the fundraiser contracts overview, it's clear that through well-defined events, error checks, and a seamless integration process, we can create a powerful fundraising mechanism on the blockchain. The combination of these concepts within Solidity showcases the potential of decentralized finance and highlights the efficiency that can be achieved through smart contracts. Moving forward, you'll be equipped to explore user interface options that can utilize this smart contract setup. You'll learn how to build an engaging user experience that will allow potential donors to easily contribute to fundraisers while keeping our platform transparent and. In today's tutorial, we're going to explore the implementation of the Fundraiserfactory, an essential component for managing multiple fundraiser contracts within a decentralized fundraising platform. This will help streamline the creation and management of fundraising campaigns. So far, we've learned about the creation and functionality of the fundraiser contract, focusing on how it manages donations and withdrawals in a decentralized fundraising platform. We explored the contract's code, including key functions for donating and withdrawing funds, and discussed the importance of event handling for transparency. Additionally, we introduced the factory contract pattern to simplify the creation of multiple fundraiser contracts while ensuring proper testing measures are in place. Moving forward, we'll delve into user interface options that enhance donor engagement and platform transparency. Now let's take a look at how we implement the Fundraiserfactory contract. This contract begins by importing the necessary fundraiser contract, which it will manage. We create an array called fundraisers to keep track of all the fundraiser instances we create. By declaring an event called fundraiser created, we enable the contract to notify observers whenever a new fundraiser is deployed, enhancing overall transparency. Next, we define the create fundraiser function, which is the core of our factory. Whenever this function is called, a new instance of the fundraiser contract is created, and the address of the caller, MSG sender, is passed to the fundraiser's constructor, establishing them as the beneficiary. This dynamic assignment is crucial as it allows each fundraiser to have a unique beneficiary, facilitating individual donation tracking. Moreover, after creating the new fundraiser, we store it in our fundraisers array and emit the fundraiser created event with the new fundraiser address. This entire process not only simplifies the creation of fundraising campaigns, but also ensures that users receive real-time notifications about their contracts, significantly improving user interaction and transparency within the platform. Now let's take a look at the Create Fundraiser function within our Fundraiserfactory contract. This function acts as the gateway for creating new fundraiser instances. When a user calls this function, it initializes a new fundraiser contract by passing the caller's address, MSG sender, as an argument to the fundraiser's constructor. This setup ensures that the individual initiating the fundraising campaign is designated as the beneficiary, which adds a layer of personalization to each fundraiser. Upon instantiation of the fundraiser contract, the newly created instance is added to the fundraisers array, allowing us to keep track of all fundraising campaigns in an organized manner. This is crucial for later retrieval and management of these contracts. Furthermore, the function emits a fundraiser-created event, providing a notification that can be captured by front-end applications. This not only enhances transparency, but also engages users by informing them when their campaign goes live. The encapsulated logic of this function exemplifies the factory pattern's ability to streamline the creation of multiple fundraising campaigns while maintaining clarity and organization within the process. Next, we will implement a function that will enable us to retrieve the total number of fundraisers created through our factory contract. This is crucial for both backend data management and user interface dynamics. The function, named getFundraiserCount, is designed to be publicly accessible, allowing anyone to call it and receive information without requiring any input parameters. When we access this function, it simply returns the length of the fundraisers array, which holds all the instances of fundraiser contracts created by the factory. This straightforward approach gives us an up-to-date count of the fundraiser contracts available, which is essential for monitoring and managing fundraising campaigns efficiently. By incorporating this functionality, we empower users and external systems to quickly retrieve information about how many fundraising campaigns exist without unnecessary manual checks or data iteration. This streamlined method not only simplifies contract interactions, but also enhances user experience by ensuring that those interested in the platform can easily see how many fundraising campaigns are operational at any given time. Keeping our contract interactions optimized is a key factor for user satisfaction, ultimately fostering a more engaging platform. Now let's take a look at the Fundraiserfactory contract, which plays a crucial role in managing multiple fundraiser contracts. Within this contract, we define an array named fundraisers that will hold the instances of our fundraiser contracts as they are created. This structure allows us to keep track of all fundraising campaigns initiated through our factory, which is vital for effective management. Next, we'll implement the Create Fundraiser function. This function is responsible for creating a new fundraiser contract each time it's invoked by a user. By passing MSG sender to the fundraiser constructor, we ensure that the user who calls this function will be the beneficiary of the newly created fundraiser. This dynamic association between the user and their fundraiser contract enhances our platform's flexibility and user-centric design. Additionally, an important aspect of our Create Fundraiser function is the emission of the fundraiser-created event. By triggering this event, we notify external applications and observers that a new fundraiser contract has been established. This functionality is not only vital for transparency, but also integrates seamlessly with front-end interfaces, allowing users to receive real-time updates about their campaigns. Now let's discuss how we can utilize the Fundraiserfactory in practice. When a user arrives at our decentralized platform, they would interact through a user interface, whether it be a website or a mobile app. The user should see a button to create a new fundraising campaign. Upon clicking this button, the application will invoke the Create Fundraiser function of our Fundraiserfactory. In the background, this function creates a new fundraiser, assigns the user as the beneficiary, and then emits an event to inform everyone of this new instance. This is a perfect example of how smart contracts work seamlessly with front-end applications, all while maintaining transparency and security characteristics of blockchain technology. Now let's take a look at how we can implement testing for our Fundraiserfactory using the Truffle framework. In this testing script, we start by requiring the necessary artifacts for both the Fundraiserfactory and the fundraiser contracts, ensuring we can interact with them in our tests. Next, we define a new test suite for the Fundraiserfactory. Within this suite, we initialize a variable to hold our factory instance. Using the before hook, we create a new instance of the Fundraiserfactory prior to running any tests, allowing us to work with a fresh factory instance each time. We then proceed to write two essential test cases. The first test validates that calling the Create Fundraiser function successfully creates a new fundraiser contract by checking the length of the fundraisers array within the factory. This effectively confirms that our factory contract is functioning as intended. The second test checks that the fundraiser-created event is emitted during the contract creation process, validating the event logging mechanism. By ensuring both of these functionalities work correctly, we can be confident in the robustness and reliability of our factory implementation before deployment. To sum it all up, the implementation of the Fundraiserfactory allows you to create multiple fundraiser contracts efficiently, without cumbersome migrations for each instance. It encapsulates the logic for creating new fundraisers while seamlessly integrating with event handling for maximum transparency. The factory pattern not only enhances the organization and management of fundraising contracts, but also optimizes user interactions with our platform, paving the way for a smooth user experience. As we continue developing our platform, understanding and utilizing these key design patterns will help us build a robust, decentralized application poised for success in the exciting world of blockchain-based fundraising. With the understanding of how the Fundraiserfactory operates, you are now equipped to not only create and manage fundraising campaigns, but also pave the path for enhanced user experience through thoughtful integration and event handling. In the next lesson, we will take these concepts further by delving into user interface options that can boost donor engagement and ensure transparency across the platform. Stay tuned as we unravel the layers of building effective user experiences in the world of decentralized. Web3 is an exciting frontier in the world of blockchain technology, enabling developers to interact with Ethereum nodes, whether locally or remotely. This powerful toolkit comprises a collection of JavaScript libraries, allowing us to bridge the gap between our applications and the Ethereum blockchain seamlessly. As we dive into this topic, you'll see how Web3 functions as an API, facilitating communication with blockchain networks. So far, we've learned about the implementation of the Fundraiserfactory and how it streamlines the creation and management of multiple fundraiser contracts, enhancing transparency in a decentralized fundraising platform. We've examined the factory design pattern and its significance, as well as the importance of user interfaces in effective engagement and interaction. Now, we will immerse ourselves into the captivating world of Web3 and explore its functionalities, methods, and advantages. Now let's see how we can set up Web3 to connect to a local Ethereum node. First, we begin by importing the Web3 library, which provides the tools necessary to interact with the Ethereum blockchain. The crucial step here is creating a new instance of Web3, which we achieve by instantiating it with an HTTP provider that points to our local node at http://localhost 8545. This setup is mandatory because, without a provider, Web3 wouldn't know which Ethereum node to communicate with. This local setup is particularly useful for development and testing purposes, as it allows us to simulate interactions without the need for real assets. Setting up this connection is foundational for leveraging the capabilities of blockchain in our applications. By establishing this link, we pave the way for performing various operations, such as sending transactions, fetching account balances, or querying smart contracts. It's an essential first step in harnessing the power of blockchain technology in our applications. Now let's see how we can utilize the getAccounts method to interact with the blockchain. This method provides a way to retrieve a list of all the accounts that the connected Ethereum node is managing. It's essential to remember that this method will only return accounts that are currently unlocked. As a best practice when working with Ethereum, ensure that your wallet is unlocked to facilitate transactions or contract interactions. To access the accounts, we will call web3 getAccounts and use a promise to handle the asynchronous response. Once the accounts are retrieved, we can print them to the console, allowing us to verify which wallets are available for our operations. This is particularly important for developers who need to manage multiple accounts or check the status of account availability while developing decentralized applications. By running this line of code, you're taking a crucial step in bridging your application with the blockchain, as it empowers you to manage and monitor Ethereum accounts effectively while building your smart contracts or conducting transactions. Next, we will check the current block number in the blockchain using the getBlockNumber method. This is crucial for monitoring the state of the blockchain as it allows your application to stay synchronized with the latest updates. Now, let's see how we can implement this in our code. We'll use the web3 getBlockNumber function, which returns a promise that resolves to the latest block number. By chaining a then method, we can log the current block number to the console for easy visibility. Moving on, we will also look at how to fetch the balance of a specific account using the getBalance method. It's essential for developers to verify account balances, especially for real Ether transactions. To do this, we will define a constant with a specific account address and then call web3 getBalance account address. This function will retrieve the balance in Wei, which is the smallest denomination of Ether. We'll convert this balance to Ether for better readability by utilizing web3 utils from Y, making it easier to interpret the account's value. This implementation not only reinforces the importance of accuracy when dealing with addresses, but also strengthens our understanding of managing balances in the Ethereum ecosystem. Now let's implement the following code to send one Ether from one Ethereum account to another. This segment utilizes the sendTransaction method from Web3, which is essential for executing transactions on the blockchain. In our code, we specify the from address, which is the account initiating the transfer, and the to address, which is the recipient's address. It's crucial to ensure these addresses are accurate, as mistakes can result in irreversible loss of funds. The value field uses the toWei utility function to convert the amount of Ether being sent, one in this case, into Wei, which is the smallest denomination of Ether used in transaction calculations. This conversion is vital because Ethereum transactions are processed in Wei. After initiating the transaction, we append a promise to handle the response. If the transaction is successful, it logs the transaction receipt along with a unique hash, offering proof of the transaction's execution. Conversely, if the transaction fails, the error message will provide insight into what went wrong. This structured approach not only executes a transaction, but also ensures proper handling of success or failure, enhancing our application's reliability. Now let's see how we can manage the connection to our Ethereum node in Web3. First, we set the provider using the setProvider method, which allows our Web3 instance to specify which Ethereum node it should connect to. In this case, we are connecting to a local node running on port 8545. Having a proper provider set is crucial, as it directs where transaction requests and state queries are sent. Next, we'll add a useful debugging statement that logs the current provider. By using console.log with Web3 current provider, we can verify that our application is indeed connected to the intended Ethereum network or node. This step is important for ensuring that we're working in the correct environment, whether that's a local test network or the main Ethereum network. Debugging can save us from many pitfalls as we proceed with further interactions within the blockchain environment. Thus, understanding and managing your provider's settings is a foundational skill in developing with Web3. Now let's implement a promise to fetch the balance of a specific Ethereum account. In the code, we begin by creating a new promise which encapsulates the asynchronous operation of retrieving the account balance. Using the web3 getBalance method, we pass the account address and a callback function that handles both potential outcomes, success and failure. If the operation is successful, the balance is resolved and stored. On the contrary, if an error occurs, perhaps due to an invalid address or network issue, the promise will be rejected, allowing us to handle this error gracefully. Next, we proceed to chain the promise with then to access the resolved balance. Here, we log the balance to the console, converting it from Way to Ether for improved readability using the Web3 utils from Y function. In case an error was caught, we utilize the catch method to log an appropriate error message. This structured approach to handling asynchronous operations is vital for building resilient applications, ensuring that we can manage unexpected issues without crashing our code. Now that we've covered the foundational aspects of Web3 and its methods, let's briefly recap what we've learned. We explored how Web3 serves as a bridge between our applications and Ethereum nodes, allowing us to interact with the blockchain effortlessly. We took detailed looks at essential methods like get accounts, get block number, get balance, and send transaction. Moving forward, we will dive deeper into using Web3 with a front-end framework such as React, where we will connect our smart contracts to user interfaces and enhance user engagement and interactions. This journey through Web3 is just beginning. With every line of code and every transaction we make, we're not just building applications, we're actively participating in this new decentralized paradigm that opens doors to innovation and possibilities. So grab your code editor and let's build some amazing decentralized applications. Web3 offers many methods that we can use to interact with the blockchain, enabling developers to create engaging and decentralized applications. In this session, we will delve deeper into the methods provided by Web3, exploring their functionalities and how we can implement them effectively. So far, we learned about the fundamentals of Web3, which acts as a bridge between applications and Ethereum nodes through API interactions. We explored essential methods such as get accounts, get block number, get balance, and send transaction, allowing us to communicate with the blockchain effectively. Additionally, we discussed the importance of connection management and promises in handling asynchronous operations. Now, we will cover the various Web3 methods in detail, showing their practical application through code examples. Now let's take a look at how we can retrieve and display the accounts associated with our Ethereum node. We begin by invoking the getAccounts method from the Web3 library, which returns a promise containing an array of accounts. Once the promise resolves, we handle the retrieved accounts by logging them to the console with a clear message indicating that these accounts are available. It's essential to remember that these accounts must be unlocked to be accessible for transactions and interactions with smart contracts. The importance of this method lies in its role as a foundation for further interactions within the Ethereum network, as these accounts are necessary for conducting transactions, sending Ether, and executing smart contract functions. Additionally, should any errors occur during this process, like issues in connecting to the node or problems with account access, we handle them gracefully by utilizing the catch method to log the error details. This structured approach not only enhances the reliability of our code, but also aids in debugging potential issues. Next, we will write the following code to retrieve the current block number from the Ethereum blockchain using the getBlockNumber method. This code calls the Web3 getBlockNumber function, which is asynchronous and returns a promise. Upon successful retrieval of the block number, the code logs it to the console, providing immediate feedback of the current block's height. This is crucial for synchronizing your application with the latest data on the blockchain, which is vital for operations that depend on the current state, such as trading apps or decentralized finance platforms. If there's an error in fetching the block number, the catch block is set up to handle it by logging an error message, ensuring that any issues can be troubleshooted efficiently. By implementing this code, you're taking an important step towards ensuring that your application always has the most up-to-date information regarding the state of the blockchain, thereby enhancing its reliability and performance. Now let's see how we can check the balance of a specific Ethereum account using Web3. To begin, we define a variable called account address, where you should replace the placeholder with your actual Ethereum address. This address is crucial as it dictates whose balance we wish to retrieve. Next, we use the getBalance method provided by Web3, which takes the account address as an argument. When we call this method, it returns a promise that resolves with the balance in Way, the smallest denomination of Ether. To enhance readability, we utilize the fromWay utility function to convert this balance from Way to Ether. This conversion allows us to present the balance in a more understandable format for users. Finally, we handle the success scenario by logging the formatted balance to the console, while an error handler captures any issues that arise during the process, such as network errors or incorrect addresses. This structured approach ensures a smooth user experience and provides clarity on the account's financial status. Now that we can transfer Ether between accounts using the send transaction method, let's see how we can implement this in our code. In this snippet, we're initiating a transaction where Ether is sent from one Ethereum address to another. The from field specifies the sender's address, indicating which account is sending the Ether, while the to field designates the recipient's address, where the Ether will be sent. Crucially, when specifying the amount to be sent, we utilize the Web3 utils to Y function. This converts the specified amount of Ether, in this case 0.1, into WAY, which is the smallest denomination of Ether used for transactions on the blockchain. After setting up the transaction details, we invoke the sendTransaction method. This method returns a promise, which upon successful execution provides a transaction receipt. This receipt contains valuable information, including the transaction hash, that can be used to track the status of the transaction on the blockchain. However, it's important to handle potential errors gracefully. The catch block allows us to respond to any issues that arise, such as transaction failures or connectivity issues, and provides feedback via console error messages. This robustness is vital for ensuring users are informed about the state of their transactions. Now let's implement the following code to interact with a smart contract on the Ethereum blockchain. First, we define the contract's ABI application binary interface, which serves as a blueprint detailing how we can interact with the smart contract's methods. You will also need the specific address where the contract is deployed, which allows us to connect to that contract on the blockchain. Once we have the ABI and contract address, we create a new instance of the contract using Web3. This instance acts as our interface for calling the functions defined in the smart contract. It provides us access to various methods that the contract exposes, enabling us to read or manipulate data stored on the blockchain. Next, we will look at how to read values from the contract using the call method. This approach allows us to retrieve data without creating a transaction, meaning it won't consume gas, making it efficient for simply querying state variables. We will invoke the getValue method from our contract instance, log the result to the console, and handle any potential errors that may arise during this process, ensuring a smoother user experience. Now let's implement the following code to send a transaction that updates a value in a smart contract. In the code, we first call the setValue function of a smart contract, assuming it accepts an integer as its parameter. This method modifies the contract's state on the blockchain. To execute this action, we utilize the send method, indicating that we want to make a state-changing transaction rather than just a read operation. We specify the sender's address within the send method, which is essential as it informs the blockchain where the transaction is initiated from. After the transaction is sent, we handle the promise returned by the send method. If the transaction is successful, we log the transaction receipt to the console, including the transaction hash, which is crucial for tracking and confirming the transaction on the blockchain. In contrast, if an error occurs, it will be caught in the catch block, allowing for effective error handling and feedback to the user. This highlights both the functionality of state changes in smart contracts and the importance of managing transactions appropriately within the blockchain ecosystem. Now let's implement the following mechanism for error handling when sending a transaction using Web3. This process is crucial as it ensures that users receive informative feedback should any issues arise during the transaction attempt. In our code, we begin by attempting to send Ether from one account to another, specifying the sender's address, the recipient's address, and the amount being transferred in WAY. Once the transaction is initiated, we handle its response through a promise. If the transaction is successful, we log the transaction hash to the console, which allows us to track its status on the blockchain. However, if an error is encountered during the transaction, we catch it and analyze the error message. This is where our error handling strategy shines. By checking for specific issues such as insufficient funds or invalid addresses, we provide clear and actionable feedback to the user. For example, if the user tries to send more Ether than they possess, they will receive a specific error message prompting them to check their balance. This structured approach not only enhances user experience, but also contributes significantly to the robustness of your application, effectively managing potential pitfalls in the transaction process. Now let's implement the following code to subscribe to an event emitted by our smart contract. In this example, we're setting up an event listener for a custom event called myEvent, which will allow our application to react to specific triggers within the contract. To establish this subscription, we use the contract events method specifying myEvent as the event we want to monitor. The method includes a filter object that helps limit the events we listen to. In this case, we're filtering by an index parameter named myIndexParam, targeting values of 42. This is useful because it narrows down the events we care about, ensuring more efficient processing. We also define the starting block to monitor, in this case, from block 0, which means we want to start listening from the genesis block of the blockchain. Once we've established the listener, we then attach two callback functions using the on method. The first callback handles incoming data. When the event is triggered, it logs the event details to the console, letting us know that our subscription is active and providing immediate feedback. The second callback captures and logs any errors that may occur during this subscription process, allowing us to address potential issues promptly. This event listening capability is particularly powerful in real-time applications, where immediate feedback is crucial. As we reach the end of this tutorial, we've covered the breadth of essential Web3 methods, enabling you to interact seamlessly with the Ethereum blockchain. From fetching accounts and block numbers to checking balances and interacting with smart contracts, Web3 empowers developers by providing a comprehensive toolkit to build decentralized applications. So far, we explored key methods in detail, and in our next lesson, we'll integrate these concepts with a front-end framework like React to create engaging interfaces for our decentralized applications. Get ready to take your skills to the next level as we continue this exciting journey into the world of blockchain. Let's dive right into setting up React for blockchain integration to build a decentralized application, or DApp. In this session, we'll be enhancing our front-end to create an interface that allows users to interact with the blockchain. So far, we covered various methods provided by Web3 to interact with the Ethereum blockchain. Now, we will cover how to integrate these backend capabilities with a front-end framework called React. To begin with, React is a popular JavaScript library developed by Facebook for building user interfaces, particularly for single-page applications where dynamic content updates are necessary. By utilizing React, we can create a seamless and responsive DApp interface. It's important to learn how to effectively use React along with blockchain technologies, as this combination is becoming increasingly prevalent in the world of decentralized applications. Now let's see how we can set up our development environment for the DApp. We begin by creating a new directory named GreetedApp, which will serve as the project folder for our application. Once we navigate into this directory, we need to install Truffle globally using npm, a package manager for JavaScript. Truffle will help streamline our development process for the blockchain. After installing Truffle, we will unbox the React template using the command truffle unbox react. This step is crucial because it automatically sets up a project structure with predefined directories for client management, smart contracts, migrations, and tests. Essentially, this boilerplate serves as a foundation that saves us the time and effort of manual configuration, allowing us to dive directly into application development. Inside the /client/src folder, we'll find front-end files that we can modify to suit our needs, setting the stage for building an interactive interface that connects with the blockchain. Next, we will import the Greta Smart Contract JSON file, which contains the ABI and the deployed network address necessary for interaction. This file is auto-generated during the deployment of the contract and is crucial for our React app to communicate with the blockchain. Now let's implement the component didMount lifecycle method within the app component. This method runs after the component is mounted and is the perfect place to establish our connection to the Ethereum network. First, we use a utility function to get the Web3 instance, which allows us to interact with the blockchain. Following this, we retrieve the user's Ethereum accounts and the network ID, which helps us identify which instance of our smart contract to interact with. Once we have the network ID, we can access the contract's details and create an instance of it using the ABI and the contract address from the deployed network. Finally, we save the Web3 instance, the user's accounts, and the contract instance in the component state. This setup is essential as it lays the groundwork for our app to communicate seamlessly with the Greta smart contract, enabling us to perform further actions such as fetching and updating the greeting message. Now that we have our contract instance ready, let's interact with it by fetching the greeting message stored on the blockchain. First, we will implement an asynchronous function called runExample. This function retrieves the greeting using the contract's greet method. By calling contract methods greet, call, we access the message stored in our smart contract, and once we receive the response, we update the component state with this data, allowing our application to render the greeting dynamically. Next, we need to ensure that this function runs when the application loads, so we'll call runExample inside component didMount after setting up the contract instance. This lifecycle method is the perfect place to execute any code that requires the component to be fully mounted, ensuring our greeting is fetched as soon as the DApp is ready. Finally, in the render method, we check if the Web3 instance is loaded before displaying our content. If everything is set, we output the greeting message stored in the component state, allowing users to see "Hello, World," or the default greeting defined in our smart contract right after the application starts. Now let's implement the input form that allows users to set a new greeting. We create a form containing a label and an input box, where the input's value is bound to the greeting state. To make the input interactive, we also set an onChange event that triggers the handleGreetingChange method, which updates the state whenever the user types into the input box. This provides a dynamic experience, as the input reflects any changes made by the user in real time. Next, we will add a button that users can click to submit their new greeting. When the button is pressed, it triggers the formSubmitHandler method. This method is asynchronous as it interacts with the blockchain. Here, we gather the necessary data, including the user's accounts and the contract instance, and call the setGreeting method from the smart contract, passing in the new greeting. Once the transaction is completed, runExample is called to refresh the displayed greeting on the front end, ensuring that users see their changes reflected immediately. This integration equips users with a straightforward way to interact with the smart contract and update the greeting message on the blockchain. At this point, it's crucial to run migrations to ensure that our smart contract is properly deployed. Now, let's execute the command truffle migrate reset in your terminal after navigating back to the root of your project. This command prepares and deploys the contracts to the Ethereum blockchain, updating any changes you may have made. It's essential for confirming that your smart contracts are functioning as intended within the blockchain environment. Once the migration has completed successfully, we need to shift our focus back to the front end. Next, we will run the command cd client followed by npm start. This action starts our React application, allowing it to communicate with the deployed smart contracts. Finally, we can navigate to http://localhost 3000/ in our browser to witness our DApp in action. Here, you will have the opportunity to interact with the application, fill out the input field to submit a new greeting, and observe the changes happening in real time. This integration lays the foundation for a responsive and dynamic interface, enabling users to interact seamlessly with the Ethereum blockchain through our DApp. With that setup, we've accomplished a lot. We've connected React with the Ethereum blockchain through our smart contract, allowing users to interact with it seamlessly via a simple user interface. This setup showcases how powerful the combination of React and blockchain technology can be, enabling developers to create responsive and user-friendly decentralized applications. In this tutorial, we covered the fundamental aspects of integrating React with blockchain interactions. We went from setting up the environment to handling state updates and submitting transactions on the Ethereum blockchain. Continue experimenting by adding more features, such as additional contract methods or improving the UI to make your DApp even better. So there you have it. We are now set up to create amazing DApps that live on the Ethereum blockchain, ensuring that our users can interact in real time. Happy coding, and see you in the next. Now let's take a look at the structure of our Greta smart contract in Solidity. The contract begins by declaring the Solidity version it will use and defining the Greta contract, which holds a private string variable called greeting. This variable is essential as it stores the current greeting message. In the constructor, we initialize the contract with a default greeting, which is passed as an argument during deployment. This ensures that the greeting variable is set right away with a specific value. Next, we implement the greet function, which allows anyone to retrieve the current greeting stored in the blockchain. This function is defined as public and view, meaning it can be called externally and does not alter the state of the blockchain. The real focus of user interaction comes from the setGreeting function. This public method takes a string parameter, greeting, which users can utilize to update the stored greeting. By allowing users to call this function, we create a direct way for them to change the greeting message stored on the blockchain. In summary, this smart contract effectively illustrates how user input can be accepted and stored in a decentralized manner on the Ethereum blockchain. Now let's implement the user input management functionality to enhance our DApp. We start by defining an initial state in our React component, which includes several properties related to our blockchain interaction, along with a new state variable, useInput, specifically designed to store the greeting message that users will input. This state will allow us to manage the data that the user provides seamlessly. Next, we'll set up an input field in our component's render method. This field will be tied to our user input state, ensuring that as the user types, their input is captured and reflected in the state. The input also includes an onChange handler that will trigger a method to update the user input state variable whenever a change occurs. To finalize the user interaction, we add a button labeled setGreeting, which, when clicked, will invoke a function that submits the greeting to the blockchain. In this setup, we are laying the groundwork for a responsive and interactive interface that connects user actions with our smart contracts functionality, paving the way for users to set and customize their greetings effectively. To process user input, we start by defining the handleInputChange method. This function is designed to update the user input state variable based on what the user types into the input field. Specifically, it captures the input event, retrieves the current value from the input field, and uses the setState to update user input. This straightforward approach ensures that the application is always aware of the latest user input, preparing it for submission. Next, we will implement the submitGreeting function, which is crucial for interacting with our smart contract. Here, we leverage the setGreeting method to send a transaction to the Ethereum blockchain. This function extracts the current accounts, contract, and use input from the component state, allowing the user to submit their personalized greeting. After sending the transaction, we update the greeting state with the new message and reset the user input to an empty string. This not only provides immediate feedback to the user, but also enhances user experience by reflecting their input instantly in the interface. Now let's implement the submitGreeting function. This method acts as the bridge between the user's input and the blockchain, allowing users to submit their personalized greeting. First, it extracts the necessary data from the component state, including the user's account, the smart contract instance, and the current user input, with the contract methods setGreeting, user input, send. We send a transaction to the smart contract, invoking the setGreeting function and passing the user's greeting as an argument. This transaction is executed from the user's account specified in the state. Once the greeting is successfully set on the blockchain, we want to provide immediate feedback to the user. To achieve this, we call the runExample method, which fetches the updated greeting from the smart contract and displays it in the user interface. This step ensures that the user sees their newly submitted greeting reflected in real time, enhancing interaction and user experience. Finally, to keep the input field clean for the next entry, we reset the user input state to an empty string. By structuring the function this way, we ensure that users can seamlessly update and view their greetings without refreshing the application. Now let's implement the render method to integrate both the display of the current greeting and the user input functionality. This method first checks if the Web3 instance is loaded, providing a loading message until it's ready. Once the application is prepared, we create a layout using a div container that holds all necessary elements. At the top of the component, the current greeting is dynamically displayed using the state greeting, which updates as users submit new greetings. Below this, we add an input field that binds to the state user input, allowing users to type in their personalized greeting. The field is interactive. It updates the state on every change through the onChange event, maintaining real-time synchronization with user input. Finally, we include a button that, when clicked, triggers the submitGreeting function. This structured approach enhances user experience by offering a clear view of the current state while encouraging user interaction with the blockchain. Overall, this render method effectively combines visual feedback and input mechanics, fostering seamless communication between the application and the users. Now that we've established our smart contract, let's see how we can bring user interaction into our React application. We start by introducing a new state variable named userInput alongside the existing state properties for managing the Web3 instance and the contract. This variable will capture the greeting that the user inputs, making it essential for tracking user submissions. Next, we create an input field tied to this user input state and a button that triggers the greeting submission. The onChange handler ensures that as the user types, the user input variable is updated seamlessly. This synchronization allows us to work with the user's input dynamically. Following this, we define a method called handleInputChange that will be invoked each time the input value changes. This method directly updates our state with the new user input. Once the user clicks the Set Greeting button, the submitGreeting function comes into play. It interacts with the smart contract by calling the setGreeting method, processing the inputted greeting, and sending it to the blockchain. Finally, we ensure the application reflects the updated greeting immediately by calling a method to fetch the latest greeting after the user's input has been submitted. This sequence guarantees that users have a smooth, engaging experience when interacting with our DApp. As we round out this lesson, let's recap what we covered. We implemented a way for users to submit their own greetings through the DApp, utilizing the setGreeting method on the smart contract. With each input change, we updated our state effectively and leveraged React's capabilities to create an engaging user experience. This exercise illustrates a fundamental concept of DApps, allowing users to interact with the blockchain in a decentralized manner. The beauty of blockchain lies not only in its transparency and security, but also in how it bridges the interaction of users with immutable records in a decentralized system. As we continue on this journey of developing DApps, always remember to focus on enhancing user experience through intuitive design and seamless interaction. So what's next? Well, there's still so much to explore. We could dive deeper into adding more complex functionalities, perhaps enabling users to transfer tokens or interact with multiple contracts. The possibilities are virtually endless, and it's time to unleash your creativity. Thank you for joining me in this tutorial. Remember, the world of blockchain is at your fingertips, and enabling user interactions is just the beginning. Keep developing, keep experimenting, and who knows what you might create next. Now that we've finished the contracts for our large-scale application, let's create the client side so we can have users interact with our contracts in the browser. This part of our project is crucial, as it allows users to connect with our decentralized application, DApp, and truly harness the power of blockchain technology. So far, we learned about enabling user input in our DApp, allowing users to set their own greetings using the setGreeting function from our Greeter smart contract. We established a React application that fetches and updates the greeting stored on the Ethereum blockchain and implemented user interaction through input fields and buttons. By managing state effectively, we provided users with a seamless experience of seeing their changes reflected in real time. Ultimately, this lesson highlights the core principle of DApps, facilitating decentralized user interactions with blockchain technology. Now we will cover how to create an engaging, functional fundraiser application by connecting the front-end client to the smart contracts we previously outlined. Next, we will set up our React application and configure it to interact with our smart contract. First, we use the command npx create React app fundraiser app to create a new React app. This generates a folder containing all the necessary boilerplate files for our application. After navigating to this folder with cd fundraiser app, we install ethers.js with npm install ethers. This library will enable us to communicate with the Ethereum blockchain and our smart contracts seamlessly. Now let's define our smart contracts application binary interface, ABI, in a new file called fundraiser.js. We declare a constant named fundraiser.ABI, which contains JSON representations of our contract functions, specifically donate for sending ether and get balance for retrieving total contributions. This ABI acts as a bridge between our front-end application and the Ethereum network, detailing how we can invoke specific functions on our smart contract. This setup is crucial for our application to function effectively, allowing users to interact with the Ethereum blockchain as they make donations to our fundraising effort. Now let's take a look at how we can create our Fundraiser app.js component to interact with our Ethereum smart contract. We begin by importing React along with the necessary hooks, useEffect and useState from the React library. We also import ethers.js, which will facilitate communication with the Ethereum network and the contract's ABI, allowing us to define the functions available in our contract. Next, we define the Fundraiser app functional component, initializing three pieces of state: provider, contract, and balance. The provider will manage our connection to Ethereum, while the contract will enable us to interact with our deployed smart contract. Now let's implement a useEffect hook that runs on component mount to set up our environment. Within this hook, we create an asynchronous function to instantiate the provider using Web3 provider and request connection from the user's Ethereum wallet. After obtaining the signer, we establish the contract instance using its address and ABI. Subsequently, we fetch the current balance using the fetchBalance function, which retrieves the contract balance and converts it from WAI to Ether for user-friendly display. Finally, our component returns a simple user interface displaying the total funds raised in ETH, ready for users to engage with our fundraising DApp. Now let's implement the donation functionality to allow users to contribute to our fundraiser directly through the UI. We begin by defining an asynchronous function called donate, which takes an amount parameter representing the ether the user wishes to donate. This function interacts with our smart contracts donate method by passing the amount as a value, utilizing ethers.js to parse the ether string into a value that the blockchain can understand. Once the transaction is successfully executed and confirmed, we call the fetchBalance function to update the displayed balance, ensuring the UI reflects any new contributions. Next, we need to set up the UI component that enables users to input their donation amounts. We initialize a piece of state called amount to manage the value entered by users. The UI consists of an input field where users can type in their desired donation amount and a button to trigger the donation process. By linking the inputs on-chain event to the setAmount function, we update our state with the user's input. The donate button is equipped with an on-click event that calls the donate function with the entered amount. allowing for a seamless donation experience right from the application interface. Now let's implement feedback for the donation process to enhance user experience. We start by introducing a message state using the useState hook, which will hold feedback messages for the users. Next, we redefine the donate function to set the message to an empty string at the beginning of the transaction, preparing it for new feedback. This function is asynchronous and will attempt to call the smart contracts donate method with the specified Ether amount. If the transaction is successful, we display a confirmation message indicating the amount donated. On the other hand, if an error occurs, we catch it and let the user know that the donation has failed. This approach ensures users receive immediate feedback, fostering trust and keeping them informed throughout the process. In the rendering part of the component, we add conditional rendering to display the message state below the donation button. If message contains text, it will be shown as user feedback on the screen. This visual cue is vital in guiding users through their actions, reassuring them whether their contribution was successful or if assistance is needed to retry. Now let's implement Tailwind CSS to enhance our application styling. First, we need to install Tailwind CSS by running a couple of npm commands, which will add it to our project as a development dependency, and initialize the configuration file. This setup is essential as it allows us to customize and use Tailwind's utility classes throughout our components. Next, we'll incorporate Tailwind's directives into our CSS file by adding @Tailwind base, @Tailwind components, and @Tailwind utilities. We effectively enable Tailwind CSS to provide its utility classes, which will help us style our application effortlessly. Now let's see how we can apply Tailwind CSS classes to our component for a more visually appealing interface. In our Fundraiser app component, we will wrap our content in a div that uses various Tailwind classes such as padding, background color, and shadow to create depth. We will also style our headers, paragraphs, and buttons with responsive sizes and hover effects to improve user engagement. This aesthetic enhancement not only makes the application look more modern, but also creates a user-friendly experience that encourages interactions, ultimately facilitating the funding process effectively. Next, we will write a migration script that will help us deploy our smart contract to the Ethereum network using Truffle. In the migration file, we begin by requiring our Fundraiser contract using artifacts, require, Fundraiser. This allows us to interact with the Fundraiser contract defined in our Solidity code. Then, we need to export a function that Truffle will execute when running migrations. Inside this function, we use the deployer object to perform the deployment by calling deployer, deploy Fundraiser. This command instructs Truffle to deploy the specified contract to the blockchain, effectively making it live and accessible on the network. Now let's see how we can implement the deployment process. After creating the migration script, we need to run the migration command in the terminal, specifying the network, in this case, Rinkeby. By doing so, we initiate the deployment process, where the smart contract is compiled, deployed, and any data is set up on the blockchain. Once completed, you can update your React application's contract address, ensuring your DApp is connected to the newly deployed instance, allowing users to start donating through the interface you've created. To summarize, we've gone through several important steps in creating our Fundraiser application. We learned how to establish a connection to our smart contract using Ethers.js, built user interfaces in React to display and manage donations, and enhanced user experience through feedback systems. We even explored basic styling and touched on deploying on Ethereum's test networks. You now have the foundational knowledge to build interactive dApps. Keep exploring, keep coding, and happy. Now let's explore the smart contract that enables our fundraising application. We begin by defining a struct called Fundraiser Data, which includes essential attributes such as the fundraiser's title, the creator's address, the total amount raised, and the goal amount. This structure efficiently organizes all the necessary information for each fundraiser. Next, we introduce an array called Fundraisers, which will store multiple instances of the Fundraiser Data struct. This allows us to keep track of all fundraising campaigns created on the platform. Now, let's see how we can enable user interactions through the Create Fundraiser function. This function allows users to create new fundraisers by passing in a title and a goal. When called, it pushes a new Fundraiser Data instance into the fundraisers array, initializing total raised to 0 and assigning the creator's address to the respective field. Additionally, we implement the Get Fundraisers function. By using this function, users can retrieve the entire list of fundraisers stored in the contract, facilitating the display of active fundraising campaigns in our front-end application. It's a simple yet effective way to interact with the data stored on the blockchain, ensuring transparency and accessibility for all users. Now let's implement the fundraiser list component, which will be responsible for fetching and displaying the active fundraisers from the smart contract. We start by importing React along with the necessary hooks, useEffect, and useState. Then, we also import ethers to help with formatting our Ethereum values. Inside our component, we declare a state variable fundraisers, initialized as an empty array. This will store the fetched data from the contract. To retrieve fundraisers, we utilize the useEffect hook, which is triggered when the component mounts or whenever the contract prop changes. In this hook, we define an asynchronous function, fetch fundraisers, that calls contract get fundraisers, retrieves the data, and updates the fundraisers state with the response. Finally, we render the component. We create a heading active fundraisers and an unordered list, where we iterate over each fundraiser in the fundraisers array. For each fundraiser, we display its title, creator's address, and the total amount raised and goal, formatting both values to Ether using ethers, utils, format Ether. This structure effectively provides users with a clear overview of current fundraising campaigns, enhancing their experience with our app. Next, we will integrate the fundraiser list component into our fundraiser app.js file. This involves importing the component and ensuring that we pass the contract prop to it, enabling the fundraiser list to interact with our smart contract. In the fundraiser app component, we establish the necessary state variables for managing the Ethereum provider and the smart contract connection. Using the useEffect hook, we asynchronously initiate the Ethereum provider, request user accounts, and instantiate the contract with the contract's ABI and address. Within the component's return statement, we render a header for the DApp and include the fundraiser list component. By passing the contract state to fundraiser list, we allow it to fetch and display all existing fundraisers dynamically. This setup transforms our application into a more interactive platform, enabling users to view a live list of fundraisers, which enhances user engagement and informs potential donors about ongoing campaigns. Overall, this integration is a critical step toward building a user-friendly fundraising experience within our decentralized application. Now let's refine our Create Fundraiser function to enhance the user experience by ensuring that the fundraiser list updates immediately after a new fundraiser is created. In this implementation, we begin with the declaration of an asynchronous function named Create Fundraiser, which takes in two parameters, the title and the goal of the fundraiser. Within this function, we use a try block to handle the transaction efficiently. The first step is to call the smart contract's Create Fundraiser method, passing in the title and converting the goal to an appropriate format using ethers, utils, pass ether, ensuring the goal is expressed in Ethereum. After invoking the transaction, we use await wait, to wait for the transaction to be confirmed on the blockchain. This step is crucial for ensuring the fundraiser has been successfully created before moving forward. Once the transaction is confirmed, we call the Fetch Fundraisers function to refresh the list of fundraisers, fetching the most recent data from the blockchain without requiring a page refresh. In the event of an error during the process, the catch block captures it, logging an error message and updating the user with feedback about the failure to create the fundraiser. This flow ensures a seamless and engaging user interaction within the application. Next, let's implement the user interface for creating a new fundraiser. In our fundraiser app component, we start by managing two pieces of state, title and goal, initialized as empty strings. These states will store the values input by the user for the title and fundraising goal. The form structure is set up inside the return statement, providing an interface where users can enter the necessary details. When the user submits the form, we prevent the default form submission behavior to avoid page refresh, and instead call the Create Fundraiser function with the title and goal values. Each input field is linked to its respective state using the value attribute, while the onChange event handlers update the state as the user types. This approach ensures that the component always displays the current input values. Additionally, the form includes a submit button that, when clicked, triggers the process of creating a new fundraiser. Overall, this well-structured code enables users to input their fundraiser details seamlessly, laying the foundation for an engaging fundraising experience within our decentralized application. Now let's enhance the user experience further by adding feedback for the fundraiser creation process. To achieve this, we will introduce a piece of state called message, initialized as an empty string, to store success or error messages to relay to the user. Next, we will implement a form consisting of two input fields, one for the fundraiser title and another for the fundraising goal in Ethereum. The user's input will be captured through state variables, title and goal, which will update on every change. When the form is submitted, we prevent the default behavior and call the Create Fundraiser function, passing in the title and goal. To provide users with immediate feedback, we will update the message state based on whether the fundraiser was created successfully or if an error occurred. This message is displayed conditionally below the form, fostering clearer communication with the users. Additionally, we will integrate the fundraiser list component, ensuring that users can view the list of created fundraisers alongside our input form. This overall approach not only facilitates a seamless user experience, but also encourages interaction within our DApp. Now let's see how we can style our form to enhance the user experience while creating a fundraiser. We need to ensure that our inputs and buttons are visually appealing and functional. To achieve this, we utilize Tailwind CSS classes within our form component. Next, we will write the form element with an onSubmit event handler that prevents the default submission action and calls the Create Fundraiser function, passing in the title and goal variables. The form includes two input fields, one for the fundraiser title and another for the funding goal, both of which are required. For each input, we set attributes such as type, placeholder, and value, along with onChange handlers to update the corresponding state variables as users type. Additionally, we add styling classes to each input, such as border, P2, rounded, and M2, which create a clean and appealing design. Finally, the submit button is styled with a background color and hover effect, making it stand out. By incorporating these styles, we enhance the overall interface, making it more engaging for users as they interact with the DApp. In conclusion, we've successfully covered the essentials of interacting with our fundraiser contracts. We have set up a robust front-end to create and display multiple fundraisers. This powerful combination of smart contract data retrieval alongside user-friendly input demonstrates how to maximize the potential of decentralized applications. Always keep in mind this is just the start. You can expand functionalities, such as adding contribution tracking, allowing users to comment on fundraisers, or even incorporating real-time analytics. Your creativity is your limit. Keep building, stay curious, and enjoy the process of creating DApps that make. In today's session, we'll delve into the fascinating process of adding detailed information about each fundraiser in our Web3 application. This will enhance user experience by allowing potential donors to gather all necessary information before making a donation. So far, we've successfully constructed our Fundraiser Decentralized application, DApp, integrated a user-friendly front end with React, and enabled users to create and view fundraisers. Now we'll focus on providing more insightful details about each fundraiser to empower our users' decisions. To start, let's remember where we left off. We previously established a solid framework that allows users to interact with our smart contract through a React interface. We created a fundraiser list component that fetches and displays active fundraisers, alongside forms for users to create new fundraisers. User feedback and immediate updates have been a focal point of our application's design. Our next milestone is to present detailed information for each fundraiser, which will aid donors in their decision-making process. Now let's implement the following by ensuring Material UI is installed in our project. We'll use the command npm install at materialui/car to add the necessary library for our dialog component. This is crucial for creating the pop-up modal that displays fundraiser details. Next, we will move to our fundraiser card.js file where we'll begin by writing the import statements. Here we will bring in React, along with essential Material UI components such as button and dialog. By incorporating these imports, we set up the foundation necessary for our UI interactions and styling, allowing us to render the dialog seamlessly when a user interacts with a fundraiser card. Now let's define some styles using makeStyles. This will help us create a consistent look for our button and cards in the application. We establish properties like margins and dimensions, allowing us to maintain a tidy and professional interface throughout our fundraiser cards. With our imports and styles in place, we will proceed to manage the state of our dialog. This involves creating state variables to track whether the dialog is open or closed. By implementing functions to handle the opening and closing actions, we ensure a dynamic and engaging user experience when interacting with our fundraiser details. Now let's implement the following code to manage the visibility of our dialog. We begin by creating a state variable named open, initialized to false, which will track whether the dialog is currently displayed. To control the dialog's visibility, we define two functions, handleOpen and handleClose. The handleOpen function sets the open state to true, signaling that the dialog should be shown, while the handleClose function reverts the open state to false, hiding the dialog when the user wishes to exit. Next, we will integrate this functionality into our fundraiser card by inserting a button within the Card Actions section. This button will trigger the handleOpen function when clicked, allowing users to view more details about the fundraiser. The button is styled using the classes button class to maintain consistency with the theme of our application. When a user clicks the View More button, the dialog becomes visible, providing an interactive way to showcase additional details about each fundraiser, which enhances the overall user experience and ultimately empowers donors with the information they need to make informed decisions. Next, we will populate the dialog with details concerning the selected fundraiser. Here, we integrate the Material UI dialog component into the render method, which serves as a pop-up modal for displaying fundraising details. We set the dialog to open based on the open state, which is controlled by the handleClose function to ensure a seamless user experience when viewing multiple fundraisers. The title of the dialog dynamically features the fundraiser's name, ensuring users know exactly where their donations are headed. As we delve into the content section, we present key details such as the fundraiser's image, description, and total donations. This not only informs potential donors, but also enhances engagement through visual representation of the cause at a glance. Furthermore, we wrap up the dialog with actions, including a cancel button, which closes the modal when clicked. This structured approach to displaying fundraiser information helps users make informed decisions quickly, ultimately fostering a more intuitive interaction within the application. By integrating these features, we enhance the user experience while promoting transparency and clarity in the donation process. Now let's implement the layout for our fundraiser card that incorporates the various components we've set up. We begin by returning a structured div containing the card component from Material UI, which is styled using our defined classes. Inside the card, we use card media to display the fundraiser's image, ensuring it has a title for accessibility. Following this, we input essential information about the fundraiser in card content, including the fundraiser name, description, and total donations, all formatted using typography for consistency. Next, we add a card actions section that features a button labeled View More. When clicked, this button invokes the handleOpen function to toggle the visibility of our dialog. This dialog opens with relevant fundraiser details, including an image, and allows users to see a more engaging description coupled with total donation statistics. The dialog also incorporates actions to either close the dialog or submit a donation. By structuring the code in this manner, we create an organic flow that enhances the user experience, allowing them to effortlessly gather information and engage with the fundraiser through an intuitive interface. Next, we will implement the state management for user donations. We begin by creating a state variable called donation amount using the useState hook, which will hold the user's input for their intended donation. This variable is initialized to an empty string. Now, to facilitate user interaction, we include a form control component from Material UI, which helps in organizing the form elements and providing a consistent layout. Within the form control, we add an input label that clearly indicates the purpose of the subsequent input field, prompting users to enter their desired donation amount. The actual input field is represented by the input component. We bind this input to our donation amount state variable, allowing it to reflect any changes made by the user in real time. The onChange event handler updates the state each time the user modifies the value, ensuring that we capture their intended donation amount. Furthermore, a placeholder value of 0 is provided to guide users on the expected format for their input. This structure not only enhances the user experience, but also ensures that the necessary data is accurately captured for subsequent donation processing steps within the application. Next, we will implement the donation functionality through a submission button within our dialog. This button, when clicked, will trigger the Submit Funds function, allowing donors to commit their contributions seamlessly. To create the button, we use Material UI's button component with an onClick event handler connected to the Submit Funds method. Now let's take a look at the Submit Funds function. This asynchronous function is responsible for processing the donation by converting the entered donation amount into WAY, the smallest denomination of Ether. The conversion ensures that we correctly format the donation amount for transaction processing on the blockchain. It then calls the smart contracts donate method to facilitate the transaction, specifying the current user's account and the value being donated. Upon successfully sending the donation, a confirmation alert will thank the user for their contribution, reinforcing positive engagement. Finally, the dialog will close, enabling users to return to the fundraiser details seamlessly. This integration not only enriches user experience, but also ensures they receive immediate feedback on their actions, fostering a more interactive fundraising process. Now, let's implement the functionality for tracking user donations. We'll start by creating a state variable called user donations to store the history of donations made by the user. This variable will be updated each time a donation is successfully submitted, ensuring that we maintain an accurate record. Next, we will define a function called renderDonationsList, which will generate a visual representation of the user's donation history. This function maps over the user donations array and displays each donation in a paragraph, indicating how much the user donated. By assigning a unique key to each paragraph based on the index, we'll optimize performance and prevent potential rendering issues. Incorporating this feature not only provides a transparent view of each user's contributions, but also reinforces trust within the platform. By enabling users to easily access and review their donation history, we enhance the overall user experience. This transparency can foster a deeper connection between users and the causes they support, promoting continued engagement and contributions. As we wrap everything up, ensure you conduct thorough testing of your application. Check the dialogue functionality, donation process, and the user experience. Verify that donations are reflected correctly in the user's account, as well as in the total for each fundraiser. With these enhancements, your Fundraiser DApp becomes much more user-centric, reliably guiding potential donors, while effectively showcasing important details of each cause. Engage users, encourage contributions, and drive home the impact of their donations with well-displayed information and insights. In conclusion, adding detailed information to your fundraisers enriches the experience for users while promoting transparency in the donation process. You've transformed a basic interface into an engaging platform that empowers not just donors, but also those advocating for causes, fostering an enriching community built on trust and transparency. Now let's see how we can implement the input field for our donation amount using Material UI's text field component. First, we need to import the text field from Material UI, which allows for an easily customizable and interactive input field. Then we declare a state variable called donationAmount, initialized to an empty string, along with the setDonationAmount function to update this state as the user types in their desired donation amount. Next, we will create the text field component itself, setting its label to donationAmount. We specify the variant as outlined to give it a clean appearance. The value prop is tied to our state variable, ensuring that whatever the user inputs gets reflected here. We also add an onChange event handler that updates the donation amount state each time the user modifies the input. Setting the type to number restricts the input to numerical values, ensuring that we capture valid donation amounts. This functionality is crucial as it enhances user experience, guaranteeing that only suitable inputs are accepted for donations. Now let's implement the Submit Funds function, which plays a crucial role in handling the donation logic when a user clicks the donation button. In this function, we first convert the user's input donation amount from Ether to Y using the Web3 utils to Y function. This conversion is necessary because Ethereum transactions typically require values in Y, the smallest unit of Ether, ensuring precision in our interactions with the smart contract. Next, we initiate the donation process by calling the donate method on our smart contract. Here, we specify the user's account as the from attribute, which indicates who is sending the funds, and we set the value to the converted donation amount. This is where the actual transaction takes place. After sending the transaction, we provide immediate feedback. If the donation is successful, we show a thank you alert, close the dialog interface, and reset the donation input field to encourage further interaction. Finally, we implement error handling with a try-catch block to manage any issues that arise during the transaction process. This ensures that if something goes wrong, we log the error and notify the user with a friendly alert, enhancing the overall user experience by providing clear communication if the donation fails. Now let's integrate the donation functionality with our user interface by adding a button that triggers the donation process. We will implement a Donate button within the Dialog Actions component. This button is associated with the Submit Funds function, which we previously established to handle the donation submission process. When users click this button, it sends the specified donation amount to the smart contract, executing the donation. The button is styled using Material UI's variant and color properties, ensuring it stands out as a primary action in our dialog. Alongside the Donate button, we also provide a Cancel button, allowing users to dismiss the dialog without making a donation. This two-button setup enhances user experience by giving clear options within the dialog actions. The on-click event for the Donate button is vital, as it binds the button's action to our donation logic, ensuring smooth functionality and a direct connection from the interface to backend smart contract processes. This step is crucial in enabling users to support their favorite causes seamlessly through our application. Now let's implement the following code to listen for the donation received event emitted by our smart contract. This event serves as a notification that a donation has successfully been processed, allowing our application to respond accordingly. In this example, we use the useEffect hook to set up the listener when the component is mounted. Inside the useEffect, we define an asynchronous function called fetchData, which connects to the smart contract and subscribes to the donation received event. By specifying an empty filter and requesting events from the latest block, we ensure that we receive any recent donations. Once the event listener is set up, we listen for the data event, which will trigger every time the donation received event is emitted. Within the event handler, we extract the total donations from the event's return values. This is crucial as it indicates the updated total after each donation. By calling setTotalDonations, we update our local state, ensuring that the user interface reflects the most current donation total. This real-time feedback enhances user engagement, as donors can immediately see the impact of their contributions. Next, we'll implement the display for total donations within our application. To achieve this, we utilize the typography component from Material UI, which will render our total donation amount elegantly. We create a paragraph element that dynamically presents the total donations captured by our state variable. This ensures that users can instantly see how much has been donated to the fundraiser in real time. Now let's take a look at how the total donations variable is integrated into the typography component. By embedding total donations within the component, it allows React to automatically update and reflect any changes to the donation total whenever a new donation is processed. This dynamic display enhances user engagement, allowing donors to see their contributions' immediate impact. Ultimately, this simple addition not only provides transparency, but also creates a stronger connection between the users and the causes they support. Thus, showcasing the donation total is a crucial step in reinforcing user satisfaction and involvement in our fundraising platform. Finally, it's essential to test our implementation comprehensively. Begin by running through your application and trying to make donations to various fundraisers. Ensure that the input accepts only appropriate values and that the total donation amounts update correctly in real time. Verify the visibility and functionality of the dialog, updates upon donation, and inspect if error handling appropriately guides the user when issues arise. Testing is an essential part of development. It ensures that the user experience is smooth and that the expected outcomes align with the actual results. The more thorough your testing, the more confident you'll be in releasing your DApp for use. As we wrap up this session, we've successfully implemented the donation functionality into our Web3 application. We built an intuitive interface for users to contribute to their chosen cause, effectively communicating total funding and enhancing user engagement. The exciting part about this feature is that it connects users directly to the positive impact they can create through their donations. It's all about fostering a sense of community and purpose through our platform. Remember, understanding these concepts is crucial not just for building this feature, but also for enhancing the overall user experience in future updates to your application. Anytime you can connect users to their actions and demonstrate tangible results, you're forming a more engaging relationship between applicants and their valued causes. In the next lesson, we'll look at topics related to security and smart contracts to ensure that our platform is safe for users and that their funds are well protected. Security is key in Web3, and understanding its principles will empower you as a developer to build resilient applications. Happy coding, and I look forward to seeing you in the next. Now let's see how we can implement secure access control in our Solidity smart contract by using the ownable contract pattern provided by OpenZeppelin. In this contract, we define a variable data, which will store a numerical value that can be modified. The critical function here is setData, which allows only the owner of the contract to change the value of data. This is enforced by the onlyOwner modifier that OpenZeppelin provides, ensuring that unauthorized users cannot manipulate this crucial piece of data. This access control mechanism is vital to enhancing the security of your contract, as it prevents unwanted changes from external entities. When using the ownable contract, remember that those who deploy the contract will automatically assume the owner role, but they can later transfer ownership if needed. By integrating this pattern, we create a robust safeguard around the function that modifies critical state variables, reflecting best practices in smart contract development and emphasizing the importance of securing sensitive logic within the code. Next, we will write the following bid placement function that demonstrates how to secure an auction process against manipulation. This function allows users to place bids in the auction, ensuring that any new bid exceeds the current highest bid documented. Firstly, we use a require statement to enforce a condition that the incoming bid must be greater than the highest recorded bid. This line acts as a safeguard, preventing users from submitting bids that do not qualify, which is crucial for maintaining fairness and integrity in the auction. If a bid does not meet the required amount, the transaction is reverted with a clear message explaining why the bid was rejected. Following the requirement check, the logic to process the bid is executed, which involves updating the state of the auction by logging the bid. The bids are stored in a mapping that associates each address with its respective bid amount, allowing the contract to track individual player contributions efficiently. By implementing these checks and structures, we enhance the security of our auction and ensure a smooth and fair bidding process for all participants. This code effectively mitigates the risk of transaction ordering attacks within the auction context. Now let's implement the following code snippet to demonstrate how we can safely manage donations using Solidity. This code defines a contract called SafeMathExample, which utilizes the SafeMath library to handle arithmetic operations safely, thereby protecting against potential overflow or underflow vulnerabilities. Here, we first import the SafeMath library, providing us with functions to perform safe arithmetic. In the contract, we declare a state variable total donations that tracks the total amount of donations received. The donate function is defined to accept a donation amount as input. Inside this function, we use the add function from the SafeMath library to increment total donations by the specified amount. This ensures that if an overflow occurs, an error is thrown, preventing any unexpected behavior that could arise from improper calculations. By leveraging SafeMath in our arithmetic operation, we reinforce the contract's security while ensuring accurate financial tracking. This pattern of using libraries like SafeMath is crucial in smart contract development as it mitigates the risks associated with integer overflow and underflow, which can lead to significant vulnerabilities and financial loss. Now let's take a look at a common vulnerability in smart contracts known as reentrancy, which can lead to significant security risks if not handled properly. In the first example, we see a function designed to withdraw funds, where the withdrawal logic is flawed. Here, the contract first attempts to send the specified amount to the user's address using a call. However, the problem lies in the fact that the balance is only set to 0 after the call, which creates an opportunity for an attacker. If they can manipulate their contract to call back the original function before the state is updated, they could withdraw funds multiple times, effectively draining the contract. To prevent this, now let's implement a safer version of the withdrawal function. In the revised code, we rearrange the logic to update the user's balance to 0 before making the external call. This change ensures that any attempt to re-enter the function will result in a 0 balance, thus safeguarding against multiple unauthorized withdrawals. Such an approach enhances the overall security of the withdrawal function and ensures that the contract behaves as intended despite external interactions. Always remember to prioritize state updates before external calls to mitigate reentrancy risks effectively. Now let's see how we can implement a function to process a collection of users while managing the risk of exceeding gas limits. The function begins by accepting an array of user IDs, which allows batching multiple transactions into a single call. To ensure we don't exceed the gas limit for any single transaction, a require statement checks that the number of user IDs being processed does not exceed a predefined batch limit. This is crucial because if the batch size is too large, the transaction may fail due to running out of gas. Once the size of the array is validated, the function enters a loop that iterates through each user ID in the array. Although the processing logic for each user is marked with a comment in the code, this is where you would implement the specific actions you wish to execute for each user, such as updating records or executing transactions. By segmenting the user processing into manageable batches, we not only enhance the efficiency of our function, but also significantly reduce the potential for encountering gas limit issues, ensuring smoother transaction execution and a better user experience. Now let's take a look at how we can manage timestamp dependence in our smart contracts to enhance security. In the provided code, we define a function named eligible for reward, which checks whether a user is eligible for a reward based on the current block's timestamp. Instead of relying on a specific timestamp, the function introduces a level of tolerance by using the modulus operator with a time period of 15 seconds. This means that the eligibility is not strictly tied to a single moment, but rather spread across defined intervals. By implementing this approach, we mitigate the risk of manipulation by miners who might influence the timestamp of transactions. The logic ensures that as long as the timestamp falls within one of the permissible intervals, users can qualify for rewards, thus removing the vulnerability associated with relying solely on exact timestamps. This code exemplifies good practice by embracing flexibility and security in contract logic, ensuring that attackers can't easily exploit timing-related vulnerabilities. Through this method, we are setting a standard for creating resilient smart contracts in the dynamic and often unpredictable blockchain environment. Lastly, while these are just a few examples of vulnerabilities that can endanger your smart contract, it's crucial to stay updated on the latest security threats in the blockchain ecosystem. Regular external audits should be part of the development lifecycle before launching your contract publicly. Conduct self-audits, maintain thorough code coverage through testing, and utilize community resources like tools from OpenZeppelin or other audit frameworks available online. Wrapping up, remember that in smart contract development, asterisk security is not a feature, it is a necessity. Always audit, test, and refine your smart contracts regularly to stay ahead of potential exploits. Happy coding and stay. One of the most effective ways to enhance the security of your smart contract is by engaging an external auditor or a prominent smart contract auditing company. This process is not just about hiring someone to look over your code. It's a comprehensive strategy to catch vulnerabilities that can turn into disastrous exploits if left unchecked. Today, we are going to dive deep into the world of smart contract auditing, exploring its significance, what it entails, and how to engage auditors effectively. So far, we learned about the critical vulnerabilities associated with smart contracts, including unprotected functions, transaction ordering dependence, integer overflow and underflow, reentrancy, gas limit issues, and timestamp dependence. We discussed how to implement security measures such as appropriate use of modifiers, safe math for safe arithmetic operations, and proper state management to prevent reentrancy attacks. Additionally, we emphasized the importance of segmenting larger operations to mitigate gas limit risks and avoiding reliance on timestamps for critical logic. Continuous audits and testing are essential to ensure the security and integrity of smart contracts in the evolving blockchain ecosystem. Now we will talk about auditing smart contracts, highlighting methodologies, standards, and providing practical examples to ensure your smart contracts are not only functional but fortified against attacks. Auditing is a meticulous process that aims to scrutinize the code of a smart contract for vulnerabilities, security flaws, and logical errors. A well-conducted audit will help you capture issues that could lead to financial loss or compromise user data. Auditors typically focus on several crucial aspects, such as code correctness, security vulnerabilities, gas efficiency, and adherence to best practices. When engaging with auditors, understanding what they look for is half the work done. Now let's take a look at a basic implementation of a token contract in Solidity, which includes mint and burn functionalities. This contract uses a mapping to maintain the balances of different addresses, allowing us to track how much each user holds. In the mint function, we can see how tokens are allocated to a specified address. It's worth noting that the currently implemented version does not restrict access, meaning any user can call this function and potentially mint tokens indiscriminately. This lack of restrictions makes the contract vulnerable, as only designated roles, typically the owner, should be allowed to issue new tokens. Next, the burn function is designed to remove tokens from a user's balance. Before proceeding with the burn, it checks if the user has sufficient tokens using a require statement, which is a pattern you should regularly implement to ensure that state changes occur only when preconditions are met. By incorporating access modifiers and further checks into these functions, we can significantly enhance the contract's security and maintain a clear understanding of permissions, making it easier for auditors or future developers to navigate the code. Next, we will take a look at two implementations of a withdrawal function in a smart contract to understand how to prevent reentrancy vulnerabilities. In the first example, the withdrawal function requires the sender to have a sufficient balance before allowing the transfer of funds. However, it first performs an external call to transfer the amount to the sender and only updates the balance after that. This sequence creates a vulnerability. An attacker could repeatedly invoke the withdrawal function through the fallback function of their contract before the balance is updated, which could drain the contract's funds. To mitigate this risk, we can implement a safer version of the withdrawal function. In the second example, we first update the sender's balance before making the external call. By ensuring that the state of the contract accurately reflects the balance before any external interactions occur, we significantly reduce the risk of a successful reentrancy attack. This adjustment enhances the security of the contract and provides a robust safeguard against unintended fund loss. Through careful management of state changes in relation to external calls, we can create safer and more reliable smart contracts. Next, we will look at a sample function designed for distributing rewards to a list of recipients. In its basic form, this function accepts two parameters, an array of addresses representing the recipients and an amount of ether to be transferred to each address. It uses a loop to iterate through the list of recipients, executing a transfer of the specified amount to each address in the array. However, this approach can pose a significant risk if the list of recipients becomes too large, potentially leading to a situation where the transaction exceeds gas limits and fails. In light of this, we can enhance our function by implementing a safeguard. Now, let's see how we can improve our function by adding a requirement that limits the number of recipients to a maximum of 100. This ensures that the transactions remain efficient and within gas limits. By employing this technique, we not only enhance the function's robustness, but also align it with best practices for gas optimization, ensuring smoother execution and preventing costly transaction failures. Now let's take a look at the safe withdraw function, which demonstrates how to implement secure withdrawal functionality in a smart contract. This function begins by implementing a require statement that ensures the amount requested for withdrawal does not exceed the balance of the caller. Such a check not only prevents users from overdrawing their accounts, but also serves as a fundamental security measure against potential exploit. After confirming that the withdrawal amount is valid, the function then deducts this amount from the user's balance, ensuring that the internal state is updated before any funds are transferred. This order of operations is crucial in maintaining the integrity of the contract, as it helps mitigate risks, such as reentrancy attacks, where an external call could manipulate the state before it is updated. Finally, the function uses the transfer method to send the specified amount of ether to the caller. By ensuring clear error messages in the require statements, the function facilitates easier debugging and offers transparency, enhancing the overall quality of the code. In summary, the safe withdraw function is an essential building block for secure interactions within smart contracts. When you engage an auditing company, communication is key. To get the best results, ensure you clearly explain the business logic behind your contract, what functionalities should be emphasized, and what specific vulnerabilities you are particularly concerned about. During the audit process, expect a back-and-forth interaction where auditors may request clarifications, ask questions, or propose changes. Once the audit is complete, auditors will provide a report detailing their findings. This report should include critical vulnerabilities identified, suggested fixes, gas optimization recommendations, and overall best practices for future developments. A well-structured report not only outlines issues, but provides you with a roadmap, equipping you with the knowledge to rectify any shortcomings. Now let's take a look at how to set up and utilize Slither, a powerful static analysis tool designed for smart contracts. First, we need to install Slither using pip, which is a package manager for Python. This installation allows us to seamlessly integrate Slither into our auditing workflow, making it easier to identify potential vulnerabilities within our contracts. Once Slither is successfully installed, the next step is to run it on your contract file. By executing the command with the file name of your smart contract, Slither will initiate a comprehensive analysis. This analysis provides valuable insights by highlighting vulnerabilities such as uninitialized storage pointers and reentrancy risks. Moreover, Slither detects deviations from best practices, which can help enhance the overall quality of your code. Remember, while automated tools like Slither streamline the auditing process, they should complement, not replace, the crucial manual reviews conducted by human auditors. By incorporating Slither into your auditing routine, you fortify your contract against potential exploits and improve its security posture in the ever-evolving blockchain landscape. Lastly, remember that the blockchain is continuously evolving, and so are the techniques used for identifying vulnerabilities. Regular audits should be a standard part of your smart contract lifecycle, especially post-deployment or after any significant updates. Engaging auditors is not merely a one-time check, but rather a proactive approach to maintaining the integrity and security of your contracts. By understanding the intricacies of smart contract auditing and committing to a consistent auditing process, you position yourself to not only foster trust with your users, but also fortify your application against potential exploits. This process is painstaking but essential and will ultimately pave the way for a secure and successful smart contract deployment. In conclusion, remember that auditing is necessary for success in the world of smart contracts. Whether engaging external auditors or using automated tools, the goal is the same: Ensure your contracts operate securely and efficiently, capable of standing up to the rigors of the blockchain space. As you keep learning and coding, may your contracts be as secure as